Good morning, Prof.
Hi, Mr. Shara. Can you hear me?
Yes, Prof.
Sorry for
But
that.
today we don't have too much students, so maybe we can start.
Oh, I see. No student today.
Yeah, because of the semester break, but I will encourage them to join. We just continue our project because this is our last project.
Sure. Understand. No problem. Yes. Thank you very much. Thank you very much. Yes.
Good morning, everyone, and welcome to our visiting lecturer program. This is our last program, so today we have a special lecture based on Raman, and our facilitator from University Kebangsaan, Malaysia, Professor Chia. So please help me to welcome our today's facilitator, Professor Chia. Prof.
Okay. Thank you very much, Mr. Saria. So, thank you. Good morning. Good day to everyone. So, let me share my screen. Okay, I'll start my seminar today. So as mentioned by Mr. Saria, so this is the third instrumentations seminar or lectures about material characterizations instruments. So today I will focus on Raman spectroscopy. The previous two are XRD and also FTIR. So why I put Raman spectroscopy as the last one after the FTIR, because Raman is always it's always complementary with FTIR. So if you have these two instruments, you can actually extract a lot of useful informations from your materials or the sample you produce in your lab. So I will say Raman is a very powerful tool, but it is underutilized for many years, mainly because of the signal to noise ratio is relatively lower compared to FTIR. So today I will explain further how can you increase the Raman signal from the sample. So, and also I give you several examples on how the related materials that you can run using FTIR using Raman spectroscopy. Okay, so I'm from Material Science Program, Department of Applied Physics, University Bangsang, Malaysia. So also known as National University of Malaysia. So this is my the outline of my seminar today. So I'll give introductions about Raman spectroscopy. Then how does it work? So which is more on the working principle behind, and I will tell you a little bit on advantages and disadvantages of Raman. So from there, you know how to solve the problems of Raman or the limitations of Raman. And I'll give you examples on applications of Raman spectroscopy. Then we will go further to understand major components inside Raman spectrometer. So what are the important components that you can always tune, or you can do some changes on the components in order to get a nice signal. Then once you have the Raman spectrum or Raman spectra, then you need to know how to interpret, how to extract useful information from there. Then I will maybe briefly, if the time is allowed, then I'll briefly explain to you how to do quantifications, okay? To do the components or compound estimations in terms of the amount in your materials using Raman. Then I will focus also on micro Raman spectroscopy. So if you remember just now, I told you that Raman spectroscopy is relatively underutilized as compared to FTIR, mainly because of the low signal to noise ratio. So slowly, then when this micro Raman spectroscopy is introduced, quite a lot of people actually started to use Raman spectroscopy for their study. And there's one new or relatively new research area, which we call surface enhanced Raman spectroscopy, or we call it SERS. So this is an interesting area to look into. This is all about how to prepare metallic surface or metallic substrate that can be used to increase the signal of Raman scattering from the materials. So I'll focus also on this part later. And the last topic, I will introduce and explain to you some of the research projects we have done in the lab, and more. All of these projects are related to Raman. We use Raman to extract important or useful information for our materials. So, as I told you just now, FTIR spectroscopy and Raman spectroscopy always complement with one another. So, it's always good if you can access these two instruments, and especially when you're running a sample which are in organic form, for instance, like maybe polymers, okay, or carbons material. So that makes FTIR and Raman spectroscopy very important. So as you know, FTIR is a non-destructive technique. So and it's a very simple measurement, so very simple. So in FTIR, we are measuring the vibration frequencies of molecule. So mainly are organic, carbon to oxygen, carbon to carbon, or carbon to hydrogen bond. And the system actually utilizes infrared. And you have far infrared, mid infrared, and also near infrared. So you can actually watch the recording video. Then and different chemical bonds absorb IR light at different wavelength. So we know that different bond, carbon hydrogen, carbon oxygen bond, they will have different vibration frequency. So this frequency actually will absorb different wavelength of the infrared light. So from the absorbent of a specific frequency, then you can actually assign it into the specific functional group that will be pretty useful for you to identify what types of compound or materials you are dealing with. Okay, so in this lectures, so I'm going to explain what is Raman spectroscopy. So Raman spectroscopy is also a non-destructive technique, same like FTIR. Then it's also about vibrational modes of molecule. Okay, so you know different functional group will have different vibration frequency, so different numbers of density of electron, different dipole moment, so different strength of the bond that will contribute to different modes of vibration and also stretching. So, and in Raman, we use laser, okay, but in FTIR, you use infrared. So all are photon, okay, photon electromagnetic wave, but just at different wavelength and different frequency or different energy. So in Raman, you need laser. So either single laser or multiple laser. It really depends on the instrument that you can access. So we use monochromatic light source. So means one wavelength of laser. But maybe in one instrument, you may have more than one. You can have 1, 2, 3, or 4, or even 5. different laser. So different laser will provide different wavelength of the different wavelength. So that different wavelength of laser will give you different sensitivity and also resolution in terms of the Raman spectrum obtained from your sample. So this Raman's spectrum obtained basically is due to the Raman effect. So what is Raman effects? I will explain to you briefly later. So it's all about the interactions between the laser or the photon or we call it incident light. So there are different terminologies. Some people use photon, some people use laser, some people say light. So they are all the same actually. So in Raman, we are talking about inelastic scattering. So it means you shine the materials with laser with specific wavelength. Then means specific wavelength means specific frequency. So an energy. So the light will actually excite the materials and actually then produce a signal and captured by the detector. So that signal is due to the scattering of the material when it interacts with the laser. So it's just like FTIR give you some kind of spectrum, and we always use this as assume this as a fingerprint, okay, fingerprint for your materials. And different compound, organic compound, or different materials will have their own specific fingerprint. So from there you can do some interpretations, and you can make a fitting. Then you know what kind of functional groups, okay, is available in your sample. So this is polystyrene. Okay, this is also polystyrene. So you can see there are difference. So difference in terms of the, of course, this is a transmittance. You can also plot it into absorbent. I've explained how to convert transmittance signal of FTIR into absorbent in my previous lectures. Then in Raman, is the intensity of the scattering signal obtained by the detector. So the x-axis is a Raman shift. So it's how many, what's the magnitude of the Raman shift in terms of frequency after your material excited by the laser and produce the scattering. So the scattering signal, how much the frequency shift. Okay, the shift will give you the respective functional group inside your material. Okay, so when you talk about FTIR, Raman, XRD, it's always radiations, or call it electromagnetic wave or light of photon. So light or radiations will interact with materials in different modes. For instance, like transmission. If the material is transparent, then light or radiations can easily pass through. So this is what transmission all about. So like in FTIR, you have transmitted mode. So if the material is not really opaque, you can actually use transmission. Then if the material is possess a high refractive index, or maybe there is it does not absorb the light, then the light will be reflected. Or if the refractive index, the material contains certain level of refractive index, then the light will actually reflected. Or diffractions, let's say your material is crystalline, so all the most of the atom is arranged in order, then you have diffractions. So this is also covered in my previous two lectures about XRD. Then if the absorption coefficient is high, then the material absorb the light or radiation, then this will be one of the interactions. And in Raman, we are talking about scattering. So when the material is exposed to the radiation or the light, then it will scatter. So the detector will actually measure the signal of scattering. So this is what we have. We will discuss later in detail for Raman. So Raman scattering is really discovered by these two scientists. So Raman and Krishnan in 1928. So Raman obtained a Nobel Prize because of this observation or this discovery. So it's all about optical scattering technique, okay, and widely used for the identifications of material. So you can actually determine the composition of the materials, okay, based on the scattering signal, and also you can actually correlate it with the properties of your materials. Okay, so it's very powerful too, very straightforward, okay, very simple. So in terms of measurement, then commonly applied in material science, chemistry, even physics also, okay, physics, life science in biology, okay, medicine, okay, pharmaceutical, semiconductors, okay, even quality control in the industry. People use Raman to do online measurement of their production system, to check the impurities, okay, to check the concentration of some compound in the mixture. This is also possible. And forensic also. So in the airport custom, actually they check luggage, okay, luggages or your belongings, okay, using Raman also. So this is also one very interesting area to explore. So Raman process specifically describe the interaction of incident light with the materials, okay, with your materials in terms of the molecular vibrations and also rotations. Then because of the vibration and rotation of the molecular structures inside the materials, it will produce scattering after the material exposed to the laser, okay, the light. So it's a very powerful tools, okay, in modern spectroscopy. So in biophysics, microscopy, geochemistry, and chemistry. So this is the principle behind of Raman scattering. So when you have material, okay, the molecule inside a material will not initially, most of the time will actually remain at the ground electronic state. So they are not at the stable state, okay, at the stable state. But actually different molecule will have different levels of the excited electronic state. So when they receive enough energy, okay, the energy can be from radiations, okay, or from the laser itself, then if the molecule will excite, okay, get excited by the light or the radiations, and electron will be excited to higher energy level. But if the energy is not really the energy provided by the light or radiation is not sufficient enough, then there will be some kind of virtual state. The electron will be excited to a state which we call virtual state. Okay, it's not actually jump up to the excited electronic state, but in the middle of these two levels. So because when the electron gets excited to this stage, they are actually not stable, then they will immediately fall back, okay, return back to the ground state. So when they return back to the ground state, the energy will be released in terms of light, a photon, okay, photon. So we measure the photon produced by this recovery, okay, of the electron. So there are three different scattering. One is Rayleigh, okay, Rayleigh scattering. So whereby Rayleigh scattering is where the electron been excited and get return back to the original state. So means that there is no loss of energy or loss of frequency, change of frequency of the light. Okay, so means that the energy of the light produced, okay, the scattered light produced by this recovery is the same frequency or energy as like the source of laser provided initially. Okay, so this is because the frequency is the same, energy is the same, so we call it elastic scattering. Okay, this is an elastic scattering, and in another name we call it Rayleigh scattering. Okay, so there's no change in terms of the energy. So, and in Raman, what we are targeted is mainly on the types of scattering. We call it Stokes scattering. This is where the electron of this excited molecule, okay, excite to a virtual state, same thing like the previous one. Okay, it excite to the previous state, to virtual state. Then it relax back. Okay, relax back and to a higher vibration state. So means it go back to the ground electronic state, but slightly higher than the starting point. So means what? Means the energy produced from this, okay, from this relaxed electron, recovery electron, the energy is slightly lower. So means there are loss of energy, and loss of energy means the frequency actually drop. Okay, so you have loss of energy in this case. So, and we name it as inelastic scattering. So the energy loss means wavelength increase because energy is 1 over wavelength. So the 1 over centimeter, the wave number plotted in the Raman spectrum actually is 1 over centimeter, the unit. So means 1 over the wavelength of the incident light, the laser, minus 1 over the wavelength of the scattered light. Okay, that means you have the shift of you have the Raman shift in the graph. So this is inelastic scattering. There's another form of scattering, we call it anti-Stokes. Okay, anti-Stokes is slightly different. Okay, there are some molecule before being excited by the laser, they are already in excited mode. Okay, so means that the energy actually is higher than the initial, the ground state here. Then when you shine the laser, electron will get excited to the virtual state, then recover back to the ground state. Okay, the zero ground state. That means you have the energy produced, received, actually smaller than the energy emitted by the electron when it recover back to the ground state. So, and this is what we call super elastic scattering. So in Raman, we only consider Stokes, okay, Stokes scattering, and there will be filter to filter the Rayleigh scattering and also anti-Stokes scattering. Okay, so this is the principle behind our Raman. So it's all about interaction of laser, okay, or radiations, okay, with the molecule. It excites the molecule, electron will jump to higher energy level, okay, but the energy is not enough to go to the excited electronic state, but actually they stuck, okay, they go up, they stuck at virtual state, which is unstable. Then the electron will immediately relax and go back to the initial states. So in Stokes scattering, okay, in Stokes scattering, there will be some kind of energy loss because of when the electron go back to the ground state, the wave, the signal produced, okay, the light radiation produced is lower in terms of the energy. So this is the energy that we use to make the calculation to get the Raman shift of that particular materials. Okay, so Rayleigh scattering, no change in terms of the energy. Stokes scattering, you have loss of energy. Anti-Stokes, that you gain actually, okay, the molecule actually gain energy. Okay, but in Raman, we only take into consideration of Stokes scattering. Okay, so that means Rayleigh scattering, you have 0 in terms of Raman shift because the energy is the same. Okay, but in Stokes scattering, okay, in Raman scattering, in terms of Stokes scattering, you have positive value of Raman shift. Okay, positive value of Raman shift, but for anti-Stokes, you have negative value of Raman shift. So this is where the detector will measure in Raman spectroscopy or Raman spectrometer. Okay, so in Stokes, the scattered photon has the energy of this, which is positive in Raman shift, but in anti-Stokes, you have negative. Okay, so I think it's not really that important. You just focus on this Stokes scattering, then you know that actually you understand why normally when you have a Raman spectrum, it's plotted in Raman shift and the value is positive. Okay, so basically it's cover the same informations that I explained just now, just for maybe in different schematic. So you have light, okay, the laser, then excite molecule, electron excited to virtual state. When you recover, okay, you relax back to the ground state, you release energy. So really no change. So if you lost in terms of the frequency or the energy, then it will be Stokes scattering. Then if you gain energy, then it's anti-Stokes scattering. Okay, so what actually determine the frequency shift, the magnitude of the shift, is all about the compounds or the materials in your products. So this table actually tells you the assignments of different bands, okay, versus the frequency range. So if you have a materials, for instance, like the material contain compound with functional group of C carbon and nitrogen, then there will be very strong Raman shift. And if you go down to, for instance, like here, carbon and chlorine stretch, then this will be the Raman shift of it. So what determines the frequency of the Raman shift? The first one is electron density. Okay, so if you have high electron density, for instance, like triple bond, carbon triple bond, then you have a lot of dense share. You have 3 pairs of share electron here. Then you will very strong in Raman shift, Raman scattering. Then followed by double bond and single bond. When you have high electron density, then means the bond strength is also very high. Okay, bond strength is very high. If you have bond strength, high bond strength, then the length of the bond will also very short. This will also give you very high Raman scattering, and also high Raman shift. Then, and also vibration frequency. If the bond length is short, okay, it's low, then you have also high vibration frequency. These three characteristics give you high, strong Raman signal. So, and if you compare with FTIR, most of the time, triple bond, double bond, and also triple bond and double bond is very low in term of the signal in FTIR. So that's why I say Raman and FTIR is always complement to one another. Some compound is less active in Raman but active in FTIR, and some is active in FTIR but less active in Raman. So if you have these two instruments, then you obtain even more useful information from your materials. Okay, so there are difference. Okay, FTIR and Raman is different, so I explained to you just now. So FTIR is more on molecular absorptions. Okay, when the frequency of the infrared shine on your material is same or consistent with the vibration frequency of the molecule or functional group, then there will be absorptions. So you have the band or the peak in the FTIR spectrum. So in FTIR spectroscopy, it's actually rely on the change in dipole moment. So you need a functional group which possess permanent dipole moment. Then only it will interact with the infrared wave. Okay, electromagnetic infrared wave shine on your material. But in Raman, okay, it's not only about dipole moment, but it also depends on the change in polarizability of your materials. So if the functional group, if the compound or the functional group is polarizable, highly polarizable, then the Raman signal will be higher. Okay, then it gives you Raman shift. So FTIR and Raman they rely on different principles, but some actually overlap with one another. If you've noticed, I'll share with you later. FTIR spectrum and Raman spectrum, there are some In certain extent, the spectrum, they are similarity in terms of the spectrum, but not all. Okay, but not all. So you notice here, this is FTIR spectrum. Okay, so it's covered from rate number 400 to 4000. But in Raman shift, okay, it's also in frequency. Okay, centimeter, 1/centimeter, 400 to 4000. So some functional group actually overlap with one another. Okay, like this one, methyl, amine, okay, hydroxyl also. Then this one, isocyanide, C double bond C, or C double bond N, okay, overlapping, more or less fall at the same frequency. Okay. So FTIR, okay, IR spectroscopy is sensitive to heteronuclear nuclear functional group. Heteronuclear functional group means a molecule contains more than one or more than one types of elements. So like carbon, nitrogen, okay, carbon, oxygen. So this is good. This is sensitive in terms of IR. But in Raman, okay, Raman is more sensitive to homonuclear nuclear molecule bonds like CC bond, okay, carbon-carbon bond. That is very suitable to be used for you to use Raman. Okay, so what are the characteristics of molecule with high intensity of Raman shift? Number one, molecule with a high polarizability. Okay, it can be easily polarized, or polar molecule, like what happened in FTIR. If you have permanent dipole moment molecule, then for instance like water, okay, water molecules are polar molecules. So FTIR is a very suitable instrument. But actually, it also gives problems to FTIR, especially when your material is hygroscopic, contain high amount of water. Then FTIR, the water spectrum, the spectrum of water actually will overlap with other functional group. So this is one issue also. That's why Raman is also a good material, good instruments for hygroscopic material, for instance, like maybe cellulose material, okay, which contain high moisture content. Okay, so in Raman, polar molecule, or also large molecule. Okay, because larger the molecule, the more vibration modes it has. So it means that you have more atoms, okay, more functional group for you to detect using Raman. So these are three main characteristics of molecules in your sample. That if you have these three characteristics, the materials, your materials contain these three characteristics, then highly possible you can get good Raman spectrum from Raman spectroscopy. Okay, so this is in Raman scattering. I think I explained to you just now. So you have laser, you excite the electron to virtual state, then you can go back to the ground state, then release the produce the Raman signal, the scattering signal. And but in IR, there will be also certain level of absorptions, okay, absorption by of IR by the molecule, but there is no any excitation to the virtual state, just merely absorptions by the molecules. Okay, so the molecule absorb the IR energy, then you measure how much the transmission, okay, the transmitted, then you know, they say this molecule absorbs certain frequency of the IR, then you know that should be one specific functional group, okay, inside your material. So both Raman and FTIR are molecular, rely on molecular vibrations, okay, or rotations. So means movement of molecules in your material. So in IR spectroscopy, absorption of light energy corresponds to the vibration energy of molecule. But in Raman, the scattering of the light, okay, shifted, okay, because of the vibration energy. So the Raman shift is related to vibration energy. For this IR, the absorption is also because of vibration energy. So both, there are certain degree of overlapping between Raman and FTIR. So this table even actually summarize more details about Raman and FTIR. So Raman mainly for symmetric stretches. Okay, so C double bond, C triple bond. Okay, asymmetry structures and or band are weak, but in FTIR, you need molecular structure, functional group or molecule with asymmetry structures, or in other words, the molecule should have dipole moment, permanent dipole moment. Then standard sample holder can be used. Raman, you can actually run your sample, even the sample actually kept in glass vial or in the plastic bag. So it's also possible. But for FTIR, this is not possible. You need to prepare it in, let's say, KBR pellet form, or if you have ATR diamond, then you can put the powder, sample on ATR powder. Okay, so for Raman, and this is very important, for Raman, even your sample contains water, okay, Raman can also give you the good spectrum, even the sample actually contain water. But in FTIR, if the sample is wet, then it will be very challenging. The signal from water will disturb or overlap with signal of other functional group. And many more, okay, many more, you can just go through. Okay, so here I give you two examples of compound, mescaline and also indene. These are two functional different organic compound. The top one is IR spectrum. The bottom one in blue color is Raman spectrum. So you can see there are certain some functional group, some peak are overlapping with one another. Some not. Okay, some not. So like this one, indene, also you have quite consistent, okay, with one another, but not all. So it again go back to the theory behind, the principle, working principle behind. FTIR is based on change in dipole moment. Okay, so the absorption of IR by the materials is mainly you require the vibration mode of the molecule, and that molecule should have change in dipole moment when they're exposed to the IR wave, okay, the IR radiations. But in Raman, okay, Raman, only molecule with high polarizability will have better scattering. So, but okay, if you want to have good IR signal and also Raman signal, then your material should fulfill these two requirements. The material should have high dipole moment, okay, or change in dipole moment, or high polarizability. Then you have, okay, you have two good signal. But in reality, it's not the case. Okay, there are many materials only active in Raman, but inactive in IR. So that's why these two instruments always complement one another. Okay. So, okay, I explained about dipole moment and also polarizability. So I just want to make sure that you don't get confused. What is dipole moment and what is polarizability? So I give you this example. So water molecule, you have two hydrogen atoms and one oxygen. So the oxygens is the negative polarity, and the proton, two protons, hydrogen is positive polarity. So this give this kind of arrangement in terms of the between the two hydrogen atom and one oxygen give you the polarity. And on top of that, this oxygen atom contain two pairs of electrons, if you still remember. So these two pairs of free electron give even negative polarity at this side. Okay, so this phenomenon did give you the permanent dipole moment, okay, for water molecule. That is dipole moment. But if water molecule exposed to external electric field, okay, external electric field like this. The water molecule will not easily actually be polarized, okay, because the electron actually, electron pair actually prefer to stick closer with the oxygen atom. Okay, so water molecule, although it contain permanent dipole moment, but it cannot be easily polarized by external electric field. Okay, that is the differences between dipole moment, permanent dipole moment, and polarizability. Okay, so but just assume that this is a water molecule, okay, with the negative end and the two positive end here. So when you have external magnetic field, external electric field, the water molecule will rotate. Okay, it will rotate and align according to the field. Means the negative will actually in opposite direction of the electric field. The positive end of these two proton will actually align, okay, towards the follow in the same direction of the external electric field. So this is not the rotation of water molecule is not because of the polarizability, but this is because of the molecular rotation. Okay, so permanent dipole moment of water molecule resulting in this kind of rotations, but the rotations is not because of water molecule being polarized. No, that's not the case. So I give you this example, which is I select water as the molecule for you to differentiate what is dipole moment and what is polarizability. Okay, so again, dipole moment is important for FTIR. Okay, polarizability is important for Raman. That's why water molecule is not active in Raman because it cannot be easily polarized by any electric field. Okay, so it means that if you have the laser, okay, shine on water molecule, because it's just possess permanent dipole moment, but it cannot be polarized by the laser, so it's not active in Raman. Okay, let's go to I think we covered some basic, okay, principle about Raman spectroscopy. Let's go to the major components. This is a bit disturbing. I cannot see the title. Okay, so let's go to a major component in Raman spectroscopy. So I give you two examples. One is macro Raman. On the top is macro Raman, like this one. Okay, and another one is a micro Raman spectrometer. There are different manufacturers, okay, and even single manufacturers, they will have different model, depends on the budget you have. Some Raman spectrometer, you can install one. If you have good funding, you can install 4, okay, up to 4 laser with different wavelength. So, and why we name it micro Raman? Because actually the spectrometer installed together with one microscope. Okay, I will explain to you in more detail later for micro Raman. So now let's focus on macro Raman first. Okay, so the laser pathway is something like this. So in Raman spectroscopy, in macro Raman spectroscopy or spectrometer, you need laser source, 1 laser, 2, 3, 4, or 5. Then laser source, then the laser will shine on your sample. Okay, if your sample contain a compound or functional group or molecule, which is easily polarized, okay, or fulfill the requirement by the Raman scattering, then there will be Raman scattering signal. Okay, and the scatterings will be filtered, okay, by a couple of filter like notch filter, Rayleigh filter. So if you should remember the Rayleigh scattering, okay, Rayleigh scattering is something that we don't want because it's no information at all. Because of the wavelength, the energy is exactly the same like the laser that shine on your material. So you have filter. Then because of the scattering contain different wavelength of light, then you need to separate them. Okay, you need to separate them into different wavelength. Okay, different wavelength, or we can call it different wavelength. Then you need a grating. Okay, a grating. That grating will actually disperse. Okay, disperse the spectrum of the scattered light into different angle, and different wavelength of the light, okay, dispersed by the will be dispersed by the grating and detected by the CCD detector. Okay, then you obtain the spectrum in your computer. Okay, so let's go to one by one. So laser source is a must. You need a laser source, okay, to excite the molecules in your sample. So this is a critical component. Okay, so it's a monochromatic light, means one wavelength, one single wavelength light. So single wavelength means different color, one color. Okay, if you look at spectrum of light, okay, from red to blue, okay, higher wavelength is red. Okay, blue is shorter wavelength. Then you need to choose. Okay, so you must only need monochromatic, so one single wavelength of laser. Okay, either from visible, this is visible, okay, visible, down to near up to near IR, okay, near IR like 1060, or ultraviolet UV region. UV region is here, closer to 400, 300 nanometer. That is UV laser. So the laser light interact with your sample, okay, then you collect the scattered light produced by your sample. So commonly used like helium neon, okay, argon, diode laser, okay, neodymium, yttrium, aluminium garnet laser. So each of these laser will produce different specific monochromatic light, okay. And normal one, very common one, we will have 488, okay, 532, 635, 785. Okay, this is very common one, and it really depends on the types of laser that you choose. Okay, some laser source is very expensive, some may be more affordable. So it really depends on the budget that you have. So, and they have lifespan. For instance, like this one, green color laser is 532, okay, 532 nanometer. It maybe can last few years, okay, maybe few 10,000 hours, okay, the lifespan of it. So once you finish, okay, the lifespan, then you need to change a new one. Okay, so why you need different wavelength? Okay, why you need different laser with different wavelength? Why you cannot have only one? Then you use it for different types of material. Okay, so there are reasons of it. So why? Because laser will affect the signal intensity. Okay, so the longer the wavelength, for instance, like this 785 nanometer, the longer the wavelength, the lower the intensity. Okay, why? Because the longer the wavelength, the lower the energy of the laser. So you have lower energy of laser shining, excite your sample, then you can't actually expect much excitations. Okay, and that could lead you to low scattering signal. Okay, that is the reason one. And you may ask, then why you choose a long wavelength? Why don't you choose short wavelength? Okay, there's also reason, because if the energy is too high, for instance, like this one, 532 compared to 785, if you choose 532, if the laser energy is too high, then you may have fluorescence. Okay, fluorescence is also another limitations or another problem actually facing by Raman, because when your material exposed to laser with too high energy, it will excite actually most of the molecule, and the electron go to the excitation level, energy level. then you have fluorescence. So fluorescence signal will cover up all the Raman scattering signal. Okay, so and for information also, different wavelength, okay, suit for different types of material. And some material will have resonance, okay. Some material with specific compound, molecular compound, will have we have resonance with the laser. If the wavelength of the laser is consistent, okay, it's close to the vibrational frequency of that particular function group, then you have resonance. So you could have very nice Raman scattering. That's why when you have unknown sample, okay, we have unknown sample, you should try Raman measurement using different laser, okay, if possible, ranging from 400 to 700. Then you understand which laser should suit your material, okay. And different wavelength, different laser will have different energy, okay, as I told you just now, different energy of the radiations and different spot size, okay, because in laser, the laser pathway in Raman spectrometer involve a lot of optics, okay. So different wavelength of laser will have different spot size and also penetration depth, okay. The depth of the penetration of the laser is different. Then eventually the exposure of the materials towards this laser will be different, and different energy of the exposure will have different scattering signal, okay. And just like I told you just now, this is a fluorescence, okay, fluorescence effect. So that's why to avoid fluorescence, you should choose longer wavelength of laser. Okay, and also consequence of optic grating and so detector, and different wavelength, different detector may sensitive to certain wavelength of laser. So that's why you need to really study. Okay, you need to understand in terms of the types of laser, what kind of grating they are using, what kind of detector they're using, and from there you know you choose the right laser. Okay, and only you understand which laser suit your materials. Okay, I give example here. So the fluorescence I told you just now, if you want to avoid fluorescence, for instance, like this one, okay, this is the Raman spectrum obtained using 532 nanometer, which is a green color laser. Then, and the red one, the bottom is a red laser, 785 nanometer. So you see this background, okay, this background is very high, contributed by fluorescence, okay, contributed by fluorescence. So if you choose 785, no fluorescence, very nice background, but signal is relatively lower. So it's always a balance. You need to compromise. You cannot expect high Raman scattering signal, low background. Okay, if you want to get rid of fluorescence, you need to compromise. Okay, you need to sacrifice. You may have low signal to noise ratio or low scattering intensity. Okay, and not only the laser, the wavelength of laser that you choose, but in Raman, there are also other parameters that you need to play around. The power that you use, because laser, the laser installed in the Raman spectrometer can be adjusted. You can choose how many percent of the laser power shine on your sample. So laser power will also give you different signal. The higher the laser power, the better the scattering. But always remember, laser, this kind of laser, the power is very high. If you overuse the power, it may destroy your sample. Okay, the sample may get degraded or maybe maybe oxidized, because especially when the sample exposed to air. Okay, then the sample will burn. Actually, got a dark spot. Okay, so you need to always study not only the laser power but also the exposure time. How long the laser shine, okay, continuously on the sample will also determine how much the scattering signal that you can obtain. So there are parameters that need to play around. So in this specific example, okay, fluorescence will be the problem. Okay, so how to solve this problem? We choose longer wavelength of laser. Okay, so what is fluorescence? Okay, so I told you just now, when you have high energy laser like 532, higher energy, because the shorter the wavelength of laser, the higher energy. Okay, then the laser actually will excite. Okay, excite your material. Then the light will absorb by the molecule. Okay, excite it. Okay, then the electron go up to the electronic state. Okay, excited electronic state, not at the virtual state. Okay, not at the virtual state. So eventually, when the electron relax back, recover back to the original energy state, there will be energy released. So that is fluorescence. Okay, that is in the form of fluorescence. So how to avoid this? You need to avoid, okay, electron gets excited to electronic state. Okay, so what you want is only at the virtual state. Okay, so here the red color, the 785, okay, 785 nanometer laser is just right. Okay, it's just right. So you get less, okay, less fluorescence. Okay, so how to select? Okay, how to select which laser wavelength for you to choose? Okay, so different wavelength would give you different peak intensity. Okay, because different wavelength of laser will have different power. Okay, then as I told you just now, the longer the wavelength, the lower the intensity. Okay, intensity of the signal. Even if you use the same power, but same power of laser. So because the relationship 1 over lambda of power 4. So if you have longer wavelength, then you can imagine the intensity loss. Okay, if you choose long wavelength laser. So here I give you 3 examples. So this is obtained from this website. Okay, 3 lasers, 532, 785, 1064. So you can see the signal. Okay, the signal is completely different. Okay, if you choose 532, you have relatively low. Okay, 785 very high. Then you choose even higher, then come very low in terms of the signal. Okay, so in real scenario, as real experimental conditions or consideration, you hope that there will be some kind of resonance. Okay, resonance. If you really understand the material you're dealing with, then for instance, like if you are doing, let's say, gold, okay, gold or silver, okay, take example of gold, then the laser at wavelength around 600 would be the best for you, because the plasmon resonance, okay, of gold is around 500 to 600 nanometer. Then you may have resonant effect. Then it may enhance the signal or scattering signal. Okay, so or you should study what kind of detector that installed in the spectrometer, what kind of what types of grading, what kind of mirrors or lenses, okay, in the spectrometer. Then, and if the material, your material contains will give you some kind of fluorescence, or for one example is hygroscopic materials, which the material absorb moisture from the environment easily. Then if you run if you analyze the material using Raman at, let's say, 532 nanometer laser, then you will have big problem. You have fluorescence. Okay, if you how to avoid this, then you should choose longer wavelength laser. Okay, so next component after laser, let's go to sample holder. So as I told you just now, Raman spectroscopy as one very, I think, interesting and important advantage is you can actually analyze a sample, even the sample is kept inside a glass vial. So you can use fiber optic because laser, you can easily transmit, okay, using fiber optic probe. Then you just shine you just touch the probe on the glass vial. Then the probe will also send back the scattering signal back to the spectrometer. Then you can obtain the Raman spectrum. Okay, so sample order is crucial. Okay, so especially for, let's say, hazardous chemicals, hazardous material, you don't need to actually do sample preparations. Okay, immediately from the plastic bag. Okay, you can just analyze then to obtain the Raman spectrum. So it can be cuvettes, okay, or microscope slides, or plates, okay, even glass vial, or even plastic bag. Okay, so there are different types of sample holder supplied or provided by the instrument manufacturers. Then next one is the monochromator, or we call it grating. Okay, the grating I told you just now. When you have light scattered, okay, scattered light from your sample, because it contains the wide spectrum of wave from different wavelength. So, and the CCD detector can detect different wavelength. So means that now you need to disperse, okay, disperse the scattered light from your sample into a wide broad spectrum, okay, at specific different wavelength and detected by the to be detected by the CCD. So this is job done by the grating. So the grating will disperse, okay, disperse the wave into specific wavelength, okay, then measure by the detector, okay. So monochromator remove background and also fluorescence. So this grating not only disperse the scattered wave, but also will actually remove, okay, remove the fluorescence to a certain extent. But it really depends, because some scattering signal contain too high fractions of fluorescence, then the grating may not able to function nicely. So this is the function of grating. Okay, after the materials excite, produce scattering signal, the scattering light with a broad spectrum, okay, will be dispersed, okay, into specific wavelength and detected by the CCD. So this is the surface of the grating. Actually, is you have a repetitious pattern with very narrow grid, okay, space between the grid, then it will disperse the light into different wavelength. And detector, okay, once the light, okay, is dispersed, then it will be detected by the detector. Most of the time we use charge couple device, okay, because of high sensitivity and affordable price. Then it normally will normally couple with computer, okay. Then you have the signal, the spectrum. Then once you have the Raman spectrum, then normally you do data analysis, okay. You do interpretations, okay. So it really depends. Sometimes you may have the access of the computer installed with the manufacturer's program, the software, then it's very easier for you to do the interpretation, but not everyone have the access. So most of the time we will do it manually. Okay, I will show you a couple example later. Okay, and also other software package available, for instance, like Origin, MATLAB, or R. And some people, they have different person who have different preference. Okay, so what are examples of applications for Raman spectroscopy? Pharmaceutical. So I summarize this. So I think maybe it's too long, but I will just maybe focus on important one. In pharmaceutical, because you are dealing with drugs, and drugs compound most of the time in very trace amount, okay, very low concentration, and some compound actually not active in FTIR, okay, then you may need to try using Raman if there is a compound which contains, let's say, C double bond C, C triple bond C, then it will be much suitable for you to try using Raman. In food, okay, in food most of the time are organic material, carbon, hydrogen, oxygen, or nitrogen. Then Raman will be very, very good, like caffeine. their study actually quantified caffeine, the compositions in food or in coffee using Raman. Very interesting. Okay, then or crystallinity of PET bottle, you can quantify how much percentage of crystallinity using Raman. Not only FTIR can do the work, but Raman will also possible. And I think this is one of the very important studies using Raman is carbon materials. If you are dealing with graphene, diamond, activity carbon, graphitic carbon, then Raman is the best instrument. FTIR will not able to extract much information and differentiates graphene and graphene oxide, but Raman will do the job. Okay, Raman. So like the carbon nanotubes, okay, graphene oxide. So you can see the defects of graphene, how many layers of the graphenes, okay, and the any strains, residual of strains inside graphene. Then for semiconductor materials, silicon carbide is also one very special compound that can be detected using Raman. Then polymer, okay, not to forget polymer, polyethylene, polypropylene, okay, polyethylene terephthalate, okay, PET is also sensitive to Raman, not only FTIR. Then biological sample, I will share with you some of the some interesting study. Raman can detect and differentiate types of virus or bacteria in materials. Okay, so they have different fingerprint, so you can differentiate it using Raman. Then even gas, okay, you can use Raman to detect gas. You can use Raman for liquid sample or water. Okay, there's a compound dissolved in water can be also detected using Raman, and this is not possible for FTIR, and also many more. Okay, so I give you an example here, like titanium dioxide. So maybe some of you may have experience because titanium dioxide has been widely used in many studies. Okay, in food, in bakery, okay, in paint, in coating, in semiconductor materials, okay, in sunblock, okay, sunblocks or self-cleaning glass, let's say photocatalytic activity. So this is titanium dioxide, very popular material, a lot of applications. So and we know that titanium dioxide contain different types of polymorph, so different crystal structures. The two important structures are anatase and also rutile. Okay, so my previous lectures on XRD. So XRD can differentiate, okay, because different crystal structures, anatase and rutile. The arrangement of atom between titanium atom and also oxygen atom is different. So you can differentiate the crystal structures. So from there, you know how you can do some estimation in terms of the compositions. Same goes to titanium. Same goes to Raman. Okay, Raman can give you very nice spectrum, and they are different in terms of the scattering. Okay, the Raman shift. So even the material contains the same elements, titanium and oxygen, but because of the arrangement, okay, crystal arrangement, it gives you different vibrational modes, okay, and different vibrational modes at different frequency, okay, and when it gets polarized by the laser, it will scatter different, the scattered signal, okay, the photon at different wavelength. So from the wavelength, you convert it into Raman shift, then you have the fingerprint. Okay, you have the fingerprint. So I would say this is a very nice, very obvious difference in terms of anatase and rutile. So that means that if you have a compound or material with a mixture of anatase and rutile structures, you can easily differentiate. And if you've done measurement carefully, okay, you check, you measure, you conduct the analysis using same concentration amount of the specimen, then you may able to do quantification study to estimate how much, how is the percentage of anatase and also rutiles in your sample. Another example, which is also interesting, besides titanium dioxide, there are wide applications. Same goes to calcium carbonate also. As I think if you're aware, in paint, in pulp and paper making, people use titanium dioxide and calcium carbonate as a filler. Okay, because titanium dioxide and calcium carbonate are white in color, very bright. Okay, very bright. So if you add this material into paint or into paper as a filler, then it will not change color, okay, the color of paper or paint. So calcium carbonate also contain different types of crystal structures, okay, or three major polymorphs: pyrite, aragonite, and also calcite. Beside XRD, okay, Raman also give you very nice signal to differentiate these three types of crystal structures. So what is so important about this is I think especially in the industry, you want to do quality control. If the customer place the order actually mainly on, let's say, Veterite, calcium carbonate, you want to check the impurities of other types of crystal structures, then you can use Raman. Compare with XRD, Raman is much more simpler, and the instruments is much more cheaper compared to between XRD and Raman. And the measurement is straightforward. If you were aware, during my previous slide, you can use fiber optic directly, even with the material actually kept inside plastic or glass bottle or vial, you can directly measure. Okay, from there immediately by second or minutes, then you able to obtain the spectrum. Try to imagine if you run this analysis using XRD, how much an XRD instrument going to cost you? Million, hundred of thousand in Malaysia. So that's very expensive. And XRD require X-ray source, which is also another cost and also another preventions in terms of the safety and precautions. But Raman, laser. So laser is not that dangerous compared to X-ray. So the measurement is pretty straightforward and less sample preparations. So I think I'm not saying XRD is not important, but for this kind of applications, you can see Raman very quick. Okay, it provides you better or maybe faster analysis process for you to obtain the result and differentiate. Okay, what types of or identify what types of crystal structures of calcium carbonate in your material. Okay, there are also studies, okay, using Raman, okay, to identify types of protein, okay, types of protein in materials. So this is a study conducted. I forgot to put the link here. Okay, I will insert and I will share the slide later. So this is on the fingernail specimens. So from there, you match with the database. Okay, you do the peak identifications. Then you know what types of proteins or peptides, okay, or proteins contains inside fingernail. Okay, I will share with you maybe more later when we go to another topic later. So this is, I think, in this lecture I give you 3 examples. I think many more you can try to find. Yeah, many more. Okay, so what are the advantages of Raman spectroscopy? First, no sample preparations. If you still remember, in XRD, you need to the specimen, your sample, let's say in powder form. If the size of the powder is still big, you need to grind it into fine powder so that the orientation of the particle is random, and to maximize the diffractions, okay, the randomness of the sample. So that is the first thing you need to do when you prepare XRD sample. And the sample size is also quite big. If you have precious material, the sample holder is like a coin shape in geometry, then it requires enough amount of the sample powder in the powder form. Then If you have very less material, very precious material, then it's also quite difficult. So for XRD, you need to do sample preparations, but for Raman, it's not. You can directly measure. Even with the bottle, in a plastic bottle, you can directly measure. So normally what you need to do if you conduct this kind of measurement, you just need to measure background on the plastic bottle first, okay? Then you measure you run another scan with the area inside got the powder, then you subtract the background, then immediately you have the spectrum of the material inside the bottle. So no sample preparation is one very important advantage of Raman. Then very high spatial resolutions, especially when you use microscope, okay, micro Raman spectroscopy. You can zoom down to micron, okay, then you can measure just one tiny spot. Let's say you have one product or one material contain impurities, okay. Try to imagine you have one big material, let's say one big solid material. By naked eyes, you see one small spot, okay, of impurity. If you run XRD is not selective. You cannot actually zoom, focus on one single dot. It's not possible. But for Raman, you can do it. Then immediately you can just analyze and obtain Raman spectrum from that particular spot. Then you know what is the composition of it. Okay, so high spatial resolution and also little sample required especially when you run under microscope. Then glass does not interfere. So if you have sample in glass, you can just measure. Okay. Then common glass recipients like glass, quartz, plastic, capillary tubes are used. Okay, even for this kind of measurement. Okay, so for instance, like this one, the background I told you just now, just scan one background, okay, on the container. Let's say in this case is glass bottle. Then the raw material inside the glass bottle, then you subtract, then you have the signal. Okay, very convenient. Next, Raman spectrum of water is weak. So if you have materials, for instance, like this one, let's say it's a water soluble compound, maybe hazardous material, contain water, then you want to measure without withdraw the sample, you can immediately, you can direct measure, okay, on the bottle. So even with water, it will not disturb the signal. Again, because of less or low polarizability of water molecule. So if you remember, water is permanent dipole moment, has no permanent dipole moment, but is low in polarizability. So it's not sensitive to Raman. So Raman intensity is proportional to the concentration. So the more molecule, okay, the more molecules of the targeted compound, then definitely the greater the scattering signal. So means you can do some kind of quantitative analysis. Okay, you can do it. It's possible to do it, but okay, but you need to do it carefully, because if you still remember, I told you the Raman scattering signal determined by many parameters: laser power, exposure time, laser wavelength, okay, laser wavelength, yes, then laser power, laser wavelength, the exposure time, okay. So these three parameters will determine the intensity of the scattering signal. So if you don't do it carefully, if you conduct the measurement using different power, different exposure time, then you assume that the signal intensity is representing the concentration, then you are wrong. Okay, so I will explain briefly later. I'll give you one example how to do it. Okay, and I provide you the link, the original articles. Then if you're interested, you can read and you can try to understand. Okay, then it's possible to couple with fiber optic. Okay, fiber optic, optical fiber. Then you can do measurement on site. Okay, so like maybe in online measurement in the productions, okay, industrial process, then you can use fiber optic. So like remote in process control, monitoring, okay, process monitoring, productions. They say I was told that in oil palm mill in Malaysia, there's one that they install Raman to measure to monitor the quality of palm oil produced in the productions. Then the measurement is conducted continuously online. So they couple the fiber optic probe into the pipeline, okay, of the production system. Then they measure the oil produced in continuous flow. So they measure, they capture the spectrum from time to time without taking sample from the production. So this is a very nice idea. So when you want to measure, you want to check the quality control, then you can directly press a button, then the spectrometer will collect the spectrum from the pipeline, okay, from the pipeline to obtain the spectrum of oil products, okay, in productions. That is one interesting example. Okay, so yep, we continue for maybe another 15 minutes. Yep. Okay, so and many more. Sorry. Yeah, this is again the fluorescence. I think I will not.
Would you like to break?
Okay, can Mr. Sharia? I think we can take
10-minute break.
Sure, sure. I'll continue later.
Okay.
Thank you. Thank you.
Again, 10 minutes
Thank you.
later. Thank you. Hello everyone, we are in break now, so please stay until 2 p.m. So in the meanwhile, we'll have break, short break, okay? Thank you. Hello, Prof.
Yes, Mr. Sarah.
Like to start now?
Yes, we can
Okay,
continue.
okay,
Yes,
okay.
thank you. So maybe I can ask any questions if any from the audience. If you have question, you can just stop me. So because or else I will just talk without checking the chat box. So don't hesitate to stop me if you have anything I need my further explanation. Yes.
I have a question. Recently, normally when we do the Raman, so we can get the peak point, and we can detect detect the materials that based on the peak, right? Which
Yes.
point. But recently, I did some characterization, and I have seen that they give us also some picture.
Yes. That is yes,
So
Mrs. Sarah.
how can we explain or what should we focus on this one, bro?
Okay, so if you have pictures, then that means they're doing microscope Raman. They do mapping.
Yeah, yes, it's
They do
mapping.
mapping. They do mapping. So that is also another interesting area to go to. Means that every single pixels, the color, the pixel color that you can see from the image, one single pixel representing one spectrum measured from that single spot. So and you can you can check it this you can assign color, let's say red color representing, let's say C double bond C, so to represent a certain specific compound in that particular image. Yes.
Okay, so it's almost similar to the TEM, right?
Yes.
No, not TEM, EDX mapping.
SEM. Yes, you're right. It's using a concept of electron microscope. You use the electron to strike on every single spot, and it will give you the energy dispersive. You measure the signals from the sample.
Oh, okay, Prof. So maybe today after your in our second session, we can discuss it. Then
Yeah.
I will show the result. Then you can help me to, or maybe explain from our picture. Then it would be more easier to understand.
Yep. Sure. Sure, Mr.
Okay.
Shara. Thank you. Thank you for the question. Thank you. So I will also cover a little bit of that topic, the imaging, Raman, micro Raman imaging, during I think the second half later. Okay, so if no further questions, I will continue. So I add this slide during the 10 minutes break just now. So I just want to catch your attention is in real scenario, okay, when you have if you have the access of Raman spectrometer, you prepare your sample, then you bring your sample to the instrument, then you run the analysis. Most of the time, you have this kind of result, especially when the material is not nicely prepared. As I told you just now, if the sample is hygroscopic, it absorbs certain moisture, then or it contains some kind of dye or compound that will give you fluorescence, then this should be maybe the first few minutes or maybe the first half hour or the first 30 minutes, you need to do optimizations, okay, from the measurement. So fluorescence is always one thing, okay, fluorescence. And especially a mixture of material. For I give example, we recently involved in a project on microplastics, okay, microplastics. This is a sample obtained from river, okay, from river. Then they would like to know, they would like to identify what types of microplastics presents in what rivers. So they do some kind of like filtrations. We use a polycarbonate filter membrane. Then they filter it. Then they under microscope you can see some kind of fabric. Okay, small pieces of plastics. Okay, then they send over some sample. Okay, some sample for us. Then we measured using Raman. We can see the microplastic under microscope. Okay, then when we try to obtain the Raman spectrum, we get very high fluorescence. And after doing some study, okay, literature review, and I think we know that why they are fluorescence, because most of the plastic product in the market, like they say bottles, they say washing detergent bottles, small cup, okay, those plastic normally it contains dye, okay, coloring agent. So and many coloring agents are fluorescence, easily get fluoresced by when you run under Raman. So we have this kind of issue actually. We are actually facing this issue in the lab. So that's why I would like to focus even further how to solve fluorescence, okay, in Raman spectroscopy. We've been spending quite a long time to really optimize the signal, and luckily we find solutions, okay, that I will cover later. Okay, we find some solution to increase the signal of Raman, okay, for microplastics. So again, maybe recall a little bit. So in normal Raman, our target is Stokes, okay, Stokes scattering. So Stokes scattering, you have energy loss, okay, energy loss. It excites to virtual, the electron excite to virtual state, return back to the ground state, okay, but slightly higher in terms of energy level. So the energy released by this scattering signal is shorter in terms of the lower because in terms of the energy, longer in terms of the wavelength. So, but in at the same time also, if the selection of the laser wavelength is not correct, if you choose too short wavelength of laser, so it means the higher the energy, the higher the energy of the laser, and also you use too high power, then the molecule may receive okay, too much energy, then the electron will get excited to the electronic state, which is something that we don't want, but sometimes it happens because we don't know what kind of energy is suitable, what is the wavelength is suitable, so we don't know. So this is most of the time you have this fluorescence problem because of it over excite to the electronic state. Then when it return back, okay, the electron got return back to the ground state, it release the fluorescence. Okay, this is the reason why you have fluorescence in Raman measurement. Okay, and the longer the wavelength, okay, the longer the wavelength of laser always give you lower energy. So one of the solution is you choose lower wavelength of energy. So how to tackle this problem? There are different ways of it. So as I told you just now, something major, one big issue of Raman, and this is a reason also why Raman is relatively underutilized compared with FTIR, okay, because of the fluorescence. Although Raman is less sensitive to water, not like FTIR. FTIR is very sensitive to water. If your sample contain high water content, moisture content, it will destroy actually it will actually affect the quality of the spectrum. But although Raman is not less sensitive to water, but it's still less utilization compared to FTIR. One reason is fluorescence. Second is because of the scattering signal. Okay, the Raman scattering signal obtained from a sample actually is very low compared to the Rayleigh scattering. Okay, most of the light receiver is Rayleigh scattering. Okay, scattering with the same power or same wavelength of the laser that you provide. So less signal, okay, less weak Raman signal, and also fluorescence is these two factors are the importance and most major issue for Raman. So how to reduce fluorescence? The one, as I told you just now, use longer wavelength. Okay, like this one, 532 fluorescence. You see the background is so high. The scattering only very small, very small one. When you choose 785, yep, it nice. Okay, it's nice. The background of fluorescence is suppressed, so the signal is very high. But not necessarily the higher the better. If you go to 1064 nanometer, you basically lost most of the signal. Why? Because of the laser, the wavelength is too high. Okay, the energy is too low. Okay, so always remember the energy is inversely proportional to the wavelength. Okay, so if you choose too high, energy too low, then the scattering, the scattering is less scattering, okay, compared to long wavelength laser. So in this case, 785 will be the best. So go back again. I told you just now, most of the time, one Raman spectrometer instrument should have more than one laser. Okay, sometimes two, sometimes three, sometimes four. Okay, we have one instrument with 4 lasers in UKM. So we have the opportunity to try different wavelength before we choose the right one, okay, and further optimize the measurement to get the best spectrum. Okay, longer wavelength is the first solutions. Second, lower the laser power. Okay, if if 532 nanometer is the only laser that you have, because sometimes really you have the limitation, right? Like myself, we have one benchtop microscope Raman in the lab with only one laser, which is the 532. Why we choose 532? If can, I would like to have more, but because of budget constraint, we only purchase one, which is 532. Okay, and why I choose 532? Because 532 laser is very suitable for carbon material. So because we are doing graphene and graphene oxide and also carbon material, so we choose 532. So in my case, I have only 532. So what to do? I do not have other options, other laser to choose. Then what should I do is I should try to lower the laser power. Okay, maybe use only 0.1 millivolt. Okay, or maybe 0.5 millivolt. But because most of the time the measurement we use only maybe 1 millivolt or 2 millivolt or 5 millivolt. Okay, if the sample can withstand that power, so you need to adjust accordingly. So to avoid fluorescence, lower the laser power. But remember, if you reduce the power, also at the same time you also reduce the scattering, because the molecule receives less energy from the laser. So the energy might not enough to excite even the electron, even to the virtual energy level. You try to avoid this, okay, to use less energy of laser. But the energy is not enough to excite most of the electron go to the virtual energy states. Then what does it mean? It means that you get less scattering. So lower laser power, not necessarily enough. So because you may get less scattering. So how to improve this is you may delay, okay, extend the exposure time. Sometimes we extend up to 10 seconds. If the material is very sensitive to Raman, then you maybe just need to use 3 seconds. Then you can get very nice spectrum. But some material, they are not so sensitive. You want to avoid fluorescence, okay, you reduce the power, but at the same time, you can extend the exposure time. Those means that the laser will continuously strike on your material, okay, your sample at low power, but you allow the sample to receive more laser, and you detector will collect the scattering signal at longer period of time. So by doing so, you may able to increase the chances for you to capture the detector for the detector to capture the scattering signal. Okay, so lower laser power always come together with longer exposure time. Okay, and by doing so, you should able to avoid or reduce the fluorescence. Okay, the third one, time gate detections, is something that you strike your material with the laser, but you delay, okay, you delay the time of the detector to collect the scattered signal. Okay, scatter light. But this is very difficult to do because you don't know unless you have a very nice setup of system that you can, let's say, delay it down to 0.5 second, maybe 0.25 second. So unless you have the function of the inside the spectrometer, then you can do so. Okay. The fourth one is adding a quencher. Quencher is an additive, is a material that you can add into your sample. Okay, so that this material will absorb the fluorescence, or it will filter, or it will avoid the formation of fluorescence. For example, like metal nanoparticle like silver, gold is known to be a good conductor. So because fluorescence involve electron excitement, okay, so the electron before the electron able to form transform into fluorescent, it actually conducted by the metal. So by doing so, you can avoid the fluorescence. Or some chemicals, okay, some chemical will actually capture, okay, will capture the electron. Then from there, you can avoid the fluorescence. But a lot of work need to be done. What would be the suitable compound? What would be the right concentration of it? Okay, what would be the correct laser power, correct exposure time? So always need to do optimization. Okay, or you can use a cool detector because cool detector is less sensitive to fluorescence. Okay, if let's say the detector has a function to cool to control the temperature, the detector will actually filter out the fluorescence signal. Okay, or you can use confocal microscope. So this is always equipped in microscope microscope Raman spectroscopy. So means that you limit, okay, you limit the spots, measurement spots on your sample by just collecting a tiny spot instead of taking a large area, okay, a large area of your sample. So by doing so, you can avoid the too much fluorescent signal captured by the detector. So most of the micro Raman spectroscopy equipped with confocal. So you narrow down, okay, you limit the spot and also the depth of the measurement. So the total volume of the measurement is very small. So then you avoid, okay, capturing too much fluorescent signal. So these are 6 possible countermeasure, okay, that you can try to improve the Raman signal. But of course, in theory you can do so, but in practical is very challenging. Okay, so it needs time for you to really optimize. Okay, so I add this on purpose because in initial my lecture notes I include Rayleigh scattering, anti-Stokes scattering, and Stokes-Raman scattering, and you cannot forget this is fluorescence, and we always don't want this. Rayleigh scattering, anti-Stokes has been filtered by the notch filter, and also the Rayleigh filter, and also some actually removed by the grating. So what we want only the Stokes-Raman scattering. Okay, so and sometimes you can actually choose UV laser. Okay, UV laser. If your sample is stable to high energy laser, then you can use this because higher laser power, okay, higher wavelength and shorter wavelength of laser, higher energy. So higher energy, better scattering. Okay, if the sample is stable enough, okay, that can expose to high energy laser like UV, then you can choose that. And if your sample is sensitive to Raman, okay, it's very sensitive to Raman, then you can choose very long wavelength of laser, even go up to 1000. But always remember, the intensity of Raman scattering is is inversely proportional to the wavelength power of 4. So unless the material contain compound which is very Raman sensitive, then you can choose this. Or else you always need to come back to 532 or 633 or 785. But this region is the fluorescence sensitive region. Many materials, fluorescent dyes, okay, coloring compound, impurity in material fluoresce at this wavelength. So I don't know why, coincidentally or what, but for reasons, we always facing problem, okay, because of fluorescence. Because most of the laser 488, 532, 633, 785 is actually falling in this fluorescence region. Okay, so that's why I told you just now, if you have the access of Raman spectrometer with more laser source, then you should try each of it. Okay, each of the laser. Then from there you choose the best one. Okay, so that's for fluorescence. I hope you have some good informations. Let's go to identifications and also assignment of pigs in Raman. So I think same thing I actually present during the FTIR lectures. There are different methods. Okay, when we we send sample to Raman, then you receive the soft copy, the spectrum in soft copy, X and Y. Okay, X and Y. Then X is the Raman shift, Y is the intensity. Okay, and sometimes depends if you have the access of the computer from the machines manufacturers, the supplier. Then like this one, Omnic is from Thermo, okay, Thermo. Then Bruker, Elmer, many more. So they have dedicated, okay, very nice software for you to do the analysis. But sometimes you may not have the access. Okay, so those software, the program contain reference database. Okay, there's a reference database, very nice, very comprehensive or very complete library or database for you to do the fitting. So the interpretation becomes so simple. Okay, but if you do not have the access, then most of the time we will just refer to journal articles. Then you downloaded maybe several full papers, okay, research article, then more or less doing the same materials like yours. Then you check in the discussions what is the Raman shift, okay, representing to what. Okay, that is very common. Okay, some very common practice. So, and before you do you conduct the interpretations, you need to do some editing or polishing, or to improve the spectrum. For instance, like you do background baseline corrections, you do normalizations, or you do smoothing. Certain level of smoothing is allowed because always remember, Raman is the Stokes Raman scattering signal is way too low, okay, in terms of the intensity compared to others scattering like Rayleigh scattering. So the noise is very high actually. Okay, most of the time you receive quite like this one, quite a lot of noise actually. So you need to do some smoothing. Then only you can do peak identifications. Okay, but if you have the software, the database, okay, you have the access of the programs provided by the manufacturers, then you may have the standard database. Then you even can check percentage of similarity. This is one very powerful tools. Okay, they have the library, the database of specific compound. Then you can ask the computer to tell you what would be the most possible compound that give you the highest matching in terms of the percentage of similarity. The program can also do so. Then you can use it to calculate the intensity. You can calculate the area under the curve. Okay, for instance, like you do crystallinity estimations, then you can use area. Okay, and many more. Okay, and many more. So So I put a assumption here. Most of the student do not have the access, okay, of the kind of program. So you need to do it manually. Okay. So I listed down several useful YouTube clips. Okay, you can just visit later. I believe maybe some of you may already know how to do it, but I think just select I think 3 of the videos I found quite useful. So you can refer if you want to do baseline corrections or you want to do deconvolutions. So deconvolution is something like this. Just imagine if you have a spectrum like this, very high in terms of the noise, okay? Then, and you may see something like you have more than 3 or 4 peaks under the spectrum. Then you can use Origin Pro software, okay, to do the deconvolution to extract the possible band or peak under the spectrum. So this video actually show you the procedure. I don't think I need to spend time on the video because you can just watch it later. Then besides that, you can also do some kind of like peak fitting, okay, and also you should also learn how to plot a nice Raman spectrum. Okay, and this video also explain. I think the content actually very useful. Okay, they show you how to do it. Okay, and eventually you get a very nice and professional plotting of Raman spectrum. And to access the software, I believe maybe PSU has the access or license, or else you maybe can just try to subscribe. Okay, the license. So I think I will share the slide after this to Mr. Saria. Then I can circulate to all the audience. Okay, so go back to another important questions. Can Raman spectroscopy be used to quantify concentration of materials? So let's say I have a compound with mixture, okay, a material with mixture of compound. Then can I do it? Can I can I run the analysis? Then I can estimate the concentration of it. If can, then that will be very useful. Okay, same like FTIR, same like XRD. Also, you can do the same thing. Okay, but how about Raman? Okay, it is possible, of course, it's possible, but you need to consider the limitation or disadvantage of Raman. It can be difficult, okay, to identify Raman band for some material, especially when the material is over complicated. You have a lot of overlapping. Let's say you have a picture, let's say a material with, let's say, more than 30 compounds, especially those commercially available compound, very complicated. Okay, then you have trouble. And second one, the intensity. Okay, because the estimation of concentration always from the intensity, because Raman shift the Raman shift, the value is always fixed if you refer to the specific or respective functional group. So the only difference is the intensity. So, and we know that intensity directly proportional to the concentration. So, but not only concentration, but also laser power. I told you just now, you need to adjust the laser power in order to avoid photo bleaching, to avoid degradation, to avoid fluorescence. So laser power affect the intensity and also exposure time. Okay, the next one, the intensity also affect by the distance between the laser and sample. You know, when when the radiation travels, especially when it pass through filter, pass through mirror, all these optic pathway, it may degrade in terms of the energy. So this will also affect the intensity of the scattering signal. Third one, roughness of the sample. Because scattering is all over the direction. Okay, if you remember the first few the initial few slide, I show you the mode of interactions between radiation or light with material, transmittance, then you have refractant, okay, and scattering. Then the scattering actually is go all directions. So if you have rougher direction, definitely is even more haywire, different directions of the scattering, and this detector only capture the detector position is fixed. So, and actually it's quite far away from the surface of the sample. Scattering happen at the surface of the sample, but detector is actually sitting inside the spectrometer. So the scattering signal actually need to pass through the pathway, going through the grating, then filter, then filter, grating, then only to the detector. So that will also affect the intensity. So what does it mean? It means that you need to do measurement carefully. You need to make sure that all these parameters are constant. Okay, constant. Then on you cannot 100% constant, but at least you try your best to maximize it. Okay, then only you can do the measurement and build. Okay, you need to build the measurement protocol. So it can be difficult to obtain accurate measurement of the sample, especially to determine the concentration. That if the sample is highly scattering, okay, or turbid, okay, your sample is possess certain degree of or absorption coefficients, then you absorb the light. Then maybe different absorption level, then different scattering. So you need to do it carefully. Okay, so but okay, by saying so, all these problems or limitation is still possible. Okay, it's still possible, but what you need to do, you need to carry out multivariate analysis. Okay, so how to do is you need to make all these things constants. Okay, then you carry out measurement using known sample. Okay, sample with known concentrations. For instance, let's say you like to check certain compound in terms of concentration in noodle, for instance. Okay, in they say instant noodle in the market. So now you buy all the instant noodle, then you crush it into powder. Okay, then you know that the concentration of this compound in instant noodle is let's say at 10% from literature, let's say, or 5%. So you need to prepare sample specimen using the noodle with known concentration of that particular compound. You do some mixing of that compound in the instant noodle powder, then you carry out the measurement. You prepare a series of instant noodle powder with that particular compound. Okay, then you measure it. Okay, you obtain the Raman spectrum. Okay, then you see whether the intensity are different or proportional to the concentration of the compound that you add in. Okay, okay. Once you got it, then you will prepare the calibration curve. Then you get some sample with unknown concentration. You verify the measurement protocol and the calibration curve. Then you back calculate the estimate concentration of that particular compound. Okay, so that is one possible thing. So it means that you need to create a predictive model using known sample. Okay, this is a study actually reported in Hindawi. I think many, not only this, in many publishers, ACS, Wiley, Science Direct, Elsevier, Springer, they have many different studies. Okay, I just happen to I got this one this morning. Then I use it as an example. So this is a method developed by this research group from Brazil. they want to develop a testing method to quantify dipyron, okay, dipyrons in oral solutions. So I'm not so sure what is this, but it's just one compound, organic compound. So in this study, they developed a method. Okay, so they use Raman spectrometer. Okay, and I believe this should be a probe or fiber optic probe. It's not microscope. If you have a microscope, even better, because you just only need tiny spots of sample. So they collect the spectrum. So they compare the spectrum with the reference, okay, dipyron 500 milligrams per mil in water, drop on top of the sample holder, then they measure. Oh, yes, then they found that, okay, this compound fit with the standard library sample, okay, the database. So you know that this is sure. I assure that this spectrum, okay, the spectrum is correct compound. Okay, this is the first thing you need to do. So this is a dipyron, the chemical. Okay, the dipyron. Okay, this chemical very complicated. So if you notice from the chemical structures of this compound, you notice this compound is sensitive to Raman because you have a lot of the benzene which is rich in high in electron density. Okay, 3 pairs of double bond, then double bond C and O. Okay, and sulfur and oxygen. Okay, and also even nitrogen. Okay, nitrogen, which is asymmetry bond. So if you remember, FTIR is sensitive to asymmetry functional group, but Raman is symmetry functional group. Like nitrogen bond, carbon bond. Okay, this is Raman sensitive. So the first thing they did is they match with the standard library to confirm that this compound is correct. Okay, then they assign accordingly. Okay, they assign accordingly the wave. Okay, the Raman shift, like this one, 1,000 up to 1,600. So each are representing the right bond. Okay, C double bond C, C double bond O, C double bond C. So if you notice, when you approach from the low frequency to high frequency, you have more double bond. Okay, because of high electron density. Okay, high vibration frequency. Then they construct the calibration curve with the known concentration. Then the intensity is obtained from the Raman spectrometer. So they use principal component regressions. Okay, you can use ANOVA. You can use what kind of software? MATLAB. Okay, then you can construct this kind of you can do this kind of study. Then it plots according to the intensity. So the intensity can be specifically to one peak or a region. Okay, a region of Raman shift. For instance, I can tell the software. Okay, I can key in the range of the Raman signal from, let's say, 500 to 1,100 for the consideration of doing this fitting. Okay, so or you can have two different regions, let's say from 500 to 1,100, and you also want to consider from here to here. So you can have two separated regions for the fitting to get the best correlation coefficients. Okay, so the best definitely is one, but it's impossible to get one. If you get one, means you highly possible you cheat, because you know Raman a lot. I think you have many errors, very standard deviation is very high. So 0.95, 0.9798 should be more than enough. Okay, so this is a calibration. Then you use unknown sample, then you measure again to avoid bias. Then you check the real concentration and predicted concentration. Okay, that construct from here to here. Like you have the equation here, so you have the intensity then you just back calculate, then you have the estimated concentration. Then you calculate the relative error. So 3% is acceptable. Okay, I think 2% is good enough because the measurement is very quick. As I told you now, most of the time, the measurement could be just within 1 minute. You will never expose the laser up to more than 1 minute because eventually you may have sample degradations, or maybe most of the time you want to avoid sample degradation, so you don't expose it for too long. Okay, so this is one example of the study for you to use Raman for compositions estimation. Okay, so I think many more. I think I have maybe others example when we talk about micro Raman and also surface enhanced Raman scattering. Okay, allow me to maybe continue for another half an hour, then we can take a break. Okay, so let's go to the next topic if there is no questions from the audience. Okay, so no, let's go to micro Raman spectroscopy. So again, I want to emphasize here, in my opinion, Raman is getting popular for two reasons. Okay, especially in my own research area. The first one is graphene. This is discovery of graphene, and graphene is so popular. So many people doing graphene, doing research project related to graphene, and especially after the Nobel Prize given. Then the second one is because of surface enhanced Raman scattering. Okay, surface enhanced Raman scattering. The third one is because of micro Raman. So because micro Raman is no longer like macro Raman, which require big sample, then a big instrument, and that will actually give you a lot of difficulty. Especially you highlights the limitation of Raman spectroscopy. So in the market, there are different types of microscope Raman, or you can call it microscope Raman or micro Raman spectroscopy, and different terminology. But the most important thing is the Raman's machine equipped with a microscope. So you can just collect Raman signal from one single tiny spot. Okay, and the size of the spot depends on the objective, the lens that you have. So you have 100 times, then you can even zoom it down to a very tiny spot. Okay, so example, this is the instrument that actually owned by my university, and this is the system that we have in the lab. This is the one with 532 nanometer laser, the green laser, and this system in our research management center. We have 4 lasers, and there are many more manufacturers like this one, VTech, very advanced, very nice instrument, and Horiba and Broker. Renisho, without forget, Renisho is also very popular. Many people using this. Okay, so the concept is the same. You still need a laser. Okay, you need a laser. Then the laser will pass through filter. Okay, no, the laser will straight go to your sample. Okay, sample passing through the microscope objective, then the lens, focus lens, then your sample will receive the energy from the laser. If the energy is enough high, it will be excited to, electron will be excited to the virtual state, go back to the ground state, emit the photon, okay, the scattering, then the scattered light will go back to the focusing mirror, go to Rayleigh filter to remove the Rayleigh scattering, which is the big chunk of the laser, the power, the light being filtered out. Then what you have is only the scattered light. Then the scattered light will be dispersed by the grating okay, dispersed into different wavelength, okay, because scattered light contain electromagnetic radiation with different wavelength. So you cannot just ask the detector to detect in a big chunk of light, right? So it must be dispersed, okay, dispersed into certain angle. Then the detector will have the array, okay, array different angle will have the detector to detect specific wavelength. So you have the spectrum. Okay, so after grating, then all the light will go to the detector. So what is the additional? Additional is only the microscope. So means that the light no longer strike on the large area. The light now the laser only strike on the tiny spots because of the microscope. Okay. Advantages of this method: you do not need large sample amount. Okay, small spots is more than enough for you to get. Okay, so and second, very simple. Okay, you just put your sample on the, let's say, a glass slide. Okay, a sample holder. Then you put just like normal microscope procedure. Then you can observe. Okay, you can focus even. You can even focus. Okay, the laser to any spots that you want. Okay, so this go back to the question asked by Mr. Savia just now, the Raman imaging. So what is Raman imaging? Raman imaging is actually is a combination of many spots of Raman analysis, okay, to construct a 2D image. So every pixel is representing one Raman spectrum. So let's say I know that this compound is with this spectrum or this functional group. So I tell the computer, this functional group, please color it with green color. So whatever area contain this compound functional group will appear in green color. So you can differentiate. You can make comparison between optic, the photograph, okay, from microscope, the image from the microscope, and also the Raman image. So you have two images. One is the microscope image, one is a Raman image. Then you can do comparison and make very good discussion. Okay, so that's very interesting. Okay, so I will give you examples on studies, okay, or materials that you can use microscope Raman. First thing, graphene. I think that's why I tell you just now, graphene is one of the reasons Raman is getting popular. Okay, so, because so many people are doing it, and I was told, and also my own observation, many people buy Raman, or mainly because of they need to they conduct study use on graphene, so they need the Raman. Okay, so this is the information that you can grab from Raman when you analyze graphene. So graphene is very thin. Okay, it's mainly carbon. So single layer or few layers of graphite. Okay, graphite. Then you do exfoliations, or you can produce graphene from gas, methanol, methane, or maybe other organic compound. Some people use alcohol. Some people use alcohol, then use some kind of like organic solvent, then just to decompose the organic compound into carbon, and or use chemical vapor depositions, then to deposit graphene on top of, let's say, copper foil, okay, in the reactor, the chamber, a CVD chamber. So it depends on the method you choose. But what interesting is this kind of arrangement, because graphene possess sp2 orbital, sp2 hybridizations. So you have one empty p orbital. So it actually can helps in terms of conductivity, electron, so electrical conductivity and also heat conductivity. So very nice. And because of these benzene structures, then the modulus is also very high. So the best graphene means less defect. So means most of the carbon is arranged accordingly, like what presented in this figure. But in real case, if you try to produce or synthesize graphene using CVD, you may have some kind of like defects. Okay, defects, for instance, like maybe some dislocation, or maybe some of the carbon is not really closely bounded. Then you have maybe sp3 hybridizations. Okay, so or you have so-called defects. Okay, defects, or maybe the graphene is not really single layer, multiple layer. Those defects or imperfections can be detected using Raman. Raman is sensitive enough for graphene. So go back to my lecture notes as well. Raman is sensitive to asymmetry, bonds, carbon-carbon, carbon single bond, carbon double bond, carbon triple bond. Carbon single bond and carbon double bond is rich in graphene. So very suitable. So what are the information you can get? G-band. Okay, G-band is the most important band here. So representing the stretching vibration of the sp2 hybridized carbon. Okay, the C double bond C, C single bond C. Okay, so this is called in plane stretching vibrations. In plane, okay, in plane vibration. So maybe in my naked eyes you cannot see actually in the arrangement of this carbon atom in graphene, the two-layer graphene. Actually, they are breathing. Okay, they have they actually always stretch and they have this kind of movement. Okay, in between the atoms. So this is G-band at 1585 from frequency. Okay, the G-band. So this is the perfect, okay, the perfect graphene arrangement. Then, and this position is affected by a number of layer, okay, number of layer. So if you have layer increase, let's say 2, 3, 4, 5 layers, then actually the peak will shifted, okay, will shift to lower wave number. 1585 is the best one. If you have shift of the highest peak, then it may be due to the increase of layer. So as I told you just now, most of the time you want single layer, okay, single layer. So you can actually they have done some kind of simulation and predict, come out with an equation to estimate the number of layer. Okay, you can do so, okay, using from the Raman spectrum. Then I told you about the defects just now. Okay, the defects just now. So this is defects, D-band. So most of the time you want it as low as possible, but in reality, because no experiment is perfect, you have a lot of contamination from the air, handling, the equipment itself, the reactor itself, the chemical itself that you use for the synthesis may also contain impurities, so it will introduce D-band. Okay, so this highlight the defects. Okay, so most of the time people will make they'll calculate the intensity ratio 1D over 1G. Okay, 1D over 1G. So the lower the better. 1D over ID over IG, the ratio representing the degree of defects. So another band is important. So for graphene is 2D band. So this is a double resonant enhanced two photon lateral vibration. This is just now. This is in plane. Okay, in plane. This is lateral vibration. So this indicative of the number of layer, not the defects. Okay, number of layer. So changing shape and position. Okay, shape and position of this peak also telling you about the layer increment. So if the layer increase, then if the peak broadens or change the shape, that means layers. So if you have a broad peak from here to here, okay, that means that you have a lot of many layers of the graphene. Okay, so this is two band, so you can see it's shift and also changing in terms of the shape of it, broadening of the 2D. So monolayer is relatively sharper, bilayer, then trilayer. Okay, very nice instrument for graphene. So So D-band, quality degree of disorder. Okay, the ring breathing, this. So ID and IG, I told you just now. So for graphite is many layer of graphene before the exfoliations. Graphite is another way, another method for you to synthesize graphene. CVD is top to bottom. Then graphite is top to CVD is bottom to top. Then graphite to graphene is bottom up and top bottom. This is top bottom. So you actually exfoliate graphite into single layer of graphene. But if you convert it into oxide, then you introduce defects. So this is the defect. If you oxidize graphite using Hammer method like potassium permanganate, sulfuric acid, phosphoric acid, then you use peroxide, hydrogen peroxide, then you have a lot of oxidations. Then you expand actually you create defects because oxidations always introduce defects because you actually provide oxygen atom to the sp2 of the carbon. So you introduce impurities, then the D band will increasing. Okay, seriously compared to the graphite with less defects. Okay, so Raman is a very suitable instrument. Okay, it's a I would say the best instrument for carbon materials, especially graphene, CNT, graphene oxide, and also reduced graphene oxide. Okay, so I share with you one of our study. I think I used the same example in XRD lectures and also FDR lectures. So we combine different instrumentations to make comprehensive discussions to support our hypothesis. So in this study, we produce graphene oxide from graphite using Hammer method, Hammer chemical. I told you just now, which is sulfuric acid, phosphoric acid, potassium permanganate. So those are very strong oxidizing agent. So during the oxidation, you create defects. So the graphite, because oxygen elements, oxygen atoms are introduced into the 2D structures of graphite. So the graphite will oxidize into oxidized graphite. So the whole structure expand because of the impurities, additional elements, oxygen elements introduced into the plane. Then it become expanded. Then because according to normal Hammer protocol, you need to leave it for a few days, 3 days, okay, then to make sure that everything fully oxidized, then fully expanded. So we found that this reaction is time consuming, and also the chemical use is very high in concentration, so it's quite hazardous. So all the very aggressive chemicals, if you try to imagine sulfuric acid, potassium permanganate, then phosphoric acid, okay, and hydrochloric acid. So the concentration is way too high. So we are thinking that can we avoid using that much chemical, high concentration? We use lower concentration, and we don't leave it for 3 days. We leave it for maybe few hours, few minutes, then to see how much the expansions. And we just slightly expand the graphite using the chemical, same chemical, but less concentration and shorter time. And we use mechanical approach, which is the homogenizer, a mixer. We combine chemical and mechanical, and to see whether we can fasten the production process using mechanical, okay, after the chemical treatment, then to produce graphene oxide. Okay, so this process involves oxidations of graphite into oxidized graphite and into graphene oxide. So Raman would be one of the suitable instrument to check. So this is the graphite. Graphite initially not dispersed in water. but over the time of oxidations by the chemicals, it become slowly well dispersed up to 24 hours. Okay, so but it will still sediment after 24 hours. So maybe because of the size also, and maybe not all the graphite, not entirely oxidized. So I think this is understandable. So we use Raman to check this is graphite. You see the G band is very high, red color G band. And 2D band is also sharp. Okay, so means what? Means the defects is not so high because 1D over 1G is around 0.2 or below 0.2, because this is around 1/5 of the total height of G. So which is 0.2, the ratio between 1D to 1G. But if you notice, oxidation up to 15 minutes, okay, the G band destroyed quite significantly. Okay, significantly. So you see the 1D over 1G immediately 15 minutes up to 1 hour, then the 1D over 1G become 1.2, and it becomes stagnant. Okay, it push 1. It maintained at around 1.2. So which means actually not necessarily need to wait that long, right? Because eventually most of the defects, amount defect, if you consider 1D or 1G is representing the magnitude of the defects introduced into the graphite. So this is something that we obtain here. So we further exfoliate the 6 hours, these 6 hours, this one, we use the homogenizer, which is a Silverson mixer at 10,000 RPM. So we further exfoliate it. So this is the XRD. Okay, if you can watch back my previous lecture video, then you know why the peak is shifted. I think I can just don't maybe not explaining this. If you are interested, you can request the video from Mrs. Savia. So the graphene oxide, okay, the graphene oxide produced from after the exfoliation, you can see. So this is a graphite flakes, many layer of graphene before the oxidations. After oxidation, we use homogenizations. So these are the sample to 1 hour, 3 hours, 6 hours, 12 hours, and 24 hours. So I think from the contrast of the graphene oxide flakes, you notice that the longer the oxidation, the thinner the graphene oxide you manage to produce. I think this is quite I think this makes sense also, because maybe the oxidation is not really happen entire layer of the graphite. So you need up to 24 hours in this case. But because in our project, we actually use this graphene oxide for reinforcement in rubber gloves. So we think of maybe not necessarily need to this thin. Okay, then we actually prefer 6 hours of oxidation. So you can imagine we reduce the oxidation time using Hummer chemical from 3 days down to 6 hours. So then we carry out the homogenization for 30 minutes. Okay, then we produce graphene oxide. Okay, so they are stable. You can see here. So even after 24 hours, this 6 hours graphene oxide is stable and no sedimentations. Okay, and we actually observe it under TM. Yeah, they are thin enough actually. The graphene oxide thickness is around 1.7 nanometer, which is few layers of graphene. Okay, few layers of graphene. But because of oxidation, then I believe the thickness will be bigger. So we claim it as few layers of graphene oxide. Okay, so this is one of the example. You can use Raman for graphene and graphene oxide. And just now, Mr. Sarya asked about the imaging. Okay, Raman imagine. So this is one example, titanium dioxide, okay, and also you can do mapping. So the red color is acetaminophen, okay, and green color is acenzamide, okay, zamide, and also caffeine. So this is drugs, okay, this is drug capsule or tablets. So this is under optical microscope or camera. Okay, I believe this is optical microscope image, camera image. Then you compare with the mapping using Raman. So the instrument will not tell you what it is, but you need to do a lot of data insert, okay, or optimization. Which means that you run the mapping, okay, mapping at every single spot. Depends on the objective lens that you use. The greater the power of magnification, the smaller the pixels. But the smaller the pixel means you need to construct it more, okay, more pixel. So it's always very difficult to decide which magnification to choose. And it also depends on the scale of the material that you are looking at. Let's say as a tablet, no need, you don't need to go so small, because you want to see the entire tablet in terms of the drugs distribution, right? So maybe choose maybe 10 times of magnification should be enough. Then you run the motorized stage of the microscope will move accordingly. Then the laser will strike on every single pixels, the spot, and collect the spectrum. Then you need to tell the computer, the software, that this compound with this functional group, okay, if any spectrum contain this functional group, that color it as, let's say, blue color, then that representing caffeine. Okay, and also you can do some kind of like crystal structures differentiations. Okay, so they say titanium dioxide, nanofiber. You want to know which one is anatase, which one is rutile, because I think I showed you these spectrums, this spectra just now, anatase and rutile. Then from a mixture, you can differentiate which one, where is rutile, where is anatase. So it's just normal scanning of Raman, but it consumes a lot of time, because one image may contain more than thousands, okay, 10,000s or 100,000s of spectrum, okay, then to construct the whole image. We have done this kind of work many times, and I think from our experience, we found that for experience, our average per image at least 6 hours, 8 hours, sometimes 12 hours. Okay, so, and it also depends on the who is doing the handling, doing the analysis. Skill is also very important to choose the right laser power. Sorry, right wavelength of laser, right laser power, the right exposure time. Okay, so, and these factors actually makes you it's actually dragging the time up. So more time actually need for you to do the optimization to get the best spectrum or the image. Very interesting. I found this very convincing. If you try to imagine, if your research paper manuscript or your thesis contain this kind of informations, nobody can questions you whether your discussion is correct or not, because most of the time we use SEM, maybe microscope, optical microscope, to say this contrast, white color contrast, bright contrast are representing what compound. This rough surface is this is what. I think that is quite I think a bit superficial, not strong the justification, because we can't say the shape, the size, or the geometry of that particular particle is what, okay, is representing, let's say, caffeine. No, that is not the right discussion to do. If you have this, then nobody can questions. Okay, so try to, maybe if you have materials with mixture of different compound, try to send over, maybe not, let's say not in PSU, you can go send to over other university. Maybe you can send to UKM also, you can try to do the measurement. Okay. Okay, and some people use Raman to differentiate, actually, to identify this is bacteria. Okay, so this is a very interesting and articles and a very interesting article. So they'll collect spectrum of different bacteria, then you can tell. So what is this? So it's not really one peak representing one bacteria, no. It's a whole spectrum, okay, whole spectrum insert into the principal component regression, PCR, okay, multivariate analysis, and they will do the matching, okay. They will tell you the percentage of error. Then from the percentage, you can, I think, confidently, okay, with the low percentage of error, then you can do some kind of a discussion and to say this kind of virus or this kind of bacteria contained in the sample. That is, I think, quite many people actually doing at the moment. So, and even SARS virus also can be differentiated, okay, can be detected using Raman. You can differentiate SARS virus and other types of virus. So they are also related study. You can try to explore. Okay, so again, titanium. Okay, titanium. I think I like titanium because very common and very popular. So XRD, this is XRD. You see, XRD give you some kind of information. Nice diagram. Okay, nice spectrum. But Raman can also give you can also differentiate brutal and this. This one may take maybe few hours. Okay, depends on the steps, the scanning step that you choose. And X-ray is dangerous. Okay, expensive instrument, but Raman. Okay, in split second. Okay, maybe 10 seconds, 15 seconds of exposure time, you can collect one spectrum. So just by maybe 15 minutes, you can come up with the plotting. So try to imagine how convenient. But it really depends on materials. Not all materials can be analyzed using Raman. So, but if you understand the basic principle behind, it will be much easier for you to decide which one to go. And always good to have more result to support each other and make strong discussions. Okay, that's how you avoid questions. Okay, from reviewer or examinations.
Hello, Prof.
Okay. Yes, Mr.
I
Sarah.
think we are close to our lunch time. So can we back again at 1 p.m. in Thailand and 2 p.m. in Malaysian time? Later
Sure.
on, we have 1 hour discussion and Q&A and everything.
Sure, Mr. Sarah. Sure. So yep.
Okay, thank you, Prof. Thank you.
Thank you. Thank you, everyone. Thank you.
Okay.
See you later. I'll see you later.
Hello, Prof. Good afternoon, Prof.
Yes, Mrs. Sarah. Yes.
Yes, Prof. You can start now.
Okay, thank you. Thank you. So welcome back. So let me continue. Let's continue. Okay, I will continue for another 20 minutes. And I straight away go to the topic related to surface enhanced Raman scheduling. I promise the audience just now, I will explain, try to introduce one solutions to overcome the limitations or disadvantages of Raman, especially on the low signal to noise ratio. So there is one method, relatively new method, although the first discovery was long ago, but I can see the trend of in terms of R&D uh, on related topic about surface and Raman scattering. So I will briefly explain what is this all about. So this is I think from the title you know that this is a phenomenon that observe on surface. So the surface, a special surface with dedicated some materials that can enhance and promote Raman scattering. So a little bit of a recap about Raman spectroscopy. So we know that different chemical compound have different vibrations or rotational modes and at the frequency, different frequency. So this kind of vibration modes also depends on the environment. So what kind of environment, for instance, at temperature, and also in this case, related to our topic now is on electric field. Let's say the materials, the compound exposed to certain electric field, then or electromagnetic field, then electromagnetic field, then when laser is coming, if the laser, the frequency of the laser is consistent with the electromagnetic field surrounding the chemical compound, there will be resonance. So this resonance will significantly enhance Raman scattering. So you can obtain the spectrum actually initially without the substrate or without the enhancement. You may get zero without no signal at all. But with the substrate, the signal can be enhanced up to 10 power of 9 to 10 power of 12 times. So that is a very significant enhancement. Okay, so and we also know that different molecular different compounds or different molecular structures will have different Raman spectrum. So this is fingerprint. Okay, this is considered as a fingerprint for dedicated compound. So it's easier for us to do identifications. Okay, based on Raman. And I also told you that just now, Raman laser give you 100% of the signal of the intensity. Okay, but only 0.001% of the energy actually converted into the intensity of Raman scattering. So from this value, you roughly know how low the signal to noise ratio of in Raman spectroscopy. This is why SIRS, after the discovery of SIRS, and also graphene, so people pay more attention on Raman, and they try to develop new substrate or new method or new protocol or new instruments, okay, or to make use of Raman for different types of studies. Okay, so conventional Raman spectroscopy, the concentration of the analytical compound that you would like to analyze has to be higher than 0.01 mole. Okay, 0.01 molar. This is considered high because this is not even down to ppm. So it's almost impossible without any substrate enhancement or any enhancement factor, and Raman can give you good signal to noise ratio. So this is also, I think, one of the important disadvantages of Raman. And last one, fluorescence. If you still remember, you can't avoid fluorescence. Okay, you can avoid you can reduce the fluorescence by using lower laser power, but at the same time you lost the signal. So this is also another issue. So by introducing surface enhanced Raman scattering, this method, the intensity can be increased tremendously, okay, up to 10 power of 6. Okay, some study even able to increase up to 10 power of 12 order. And people claim that SIRS able to detect single molecule spectrum. So I'm not so sure, but I think the power of 12, 11 is something achievable. Okay, so this is all about this figure. I like this figure because it actually basically it tells you the concept of surface enhanced Raman scattering. In normal Raman spectroscopy, laser will directly strikes on the molecule and electron get excited and also scattered. Okay, in return, scattered the radiation into Raman scattering. Okay. But in SIRS, the compound actually sitting closely on the substrate. Actually, it's on the substrate containing a metal nanoparticle or metallic nanostructures. In this case, I assume this is silver. So the compound, the molecule actually close to the surface, okay, stick on the surface. So it is close to the surface of the metallic nanostructures. So we know metallic nanostructure, for instance, like silver and gold, will have surface plasmon resonance. So I'll explain to you what is that. So the surface plasmon resonance, resonate together with the laser. Okay, the laser come strike on the surface of the substrate containing the compound, and it will build extended electric field because of the enhancement by this resonance by these two factors. One is the nanoparticle surface plasmon, and also the laser with the same frequency. Okay, then resonance happen. So it builds it creates an extension of electric field. Okay, electromagnetic field on the surface of substrate that enhance the signals of the Raman scattering for the compound. Okay, so this is the whole concept of it. So you have a metallic surface with some kind of rough surface, okay, and it will enhance the signal of Raman, okay, for chemical compound. So this was discovered in 1974 by Frenchman. This is they are in the group, and they noticed this accidentally. So they noticed that when you run Raman and if you on the surface of metallic like silver electrode, then the Raman's spectrum of that particular compound will be further significantly enhanced. Then they realize that this is because of the surface plasmon resonance of the metallic silver. Okay, so there are several mechanisms proposed. There are, I think two are very, I think the most important are these two, the electromagnetic enhancement and also chemical enhancement. So electromagnetic enhancement is the electromagnetic field enhanced by the surface, as I explained to you just now. So chemical enhancement is more like electronic charges transfer. This is not so significant, but the most important one will be the electromagnetic enhancement. So look at this figure. As you know, metallic transition metal, especially silver or gold, they have free electron actually at the outer orbital. So this electron cloud will always oscillate, especially when they're exposed to electric field. So the electric field can be from, in this case, will be from the laser. So when you strike laser, okay, radiation laser on the surface, if the frequency of this laser is consistent with the surface plasmon resonance frequency, then there will be resonance happen. So, and why the resonance happen is because of the collective oscillation. So if you have the electron oscillate, the electron cloud oscillate up and down like this, and with the help of the laser, also at the more or less the same frequency range, then it will actually resonate the electron cloud. Then eventually this electron cloud will be extended up to 20 nanometer from the surface of the metallic substrate. So if this 20 nanometer region is contain organic compound, then the organic compound will also excited by the electric field and give you highest intensity signal of the Raman scattering. So this is the whole idea of surface Raman, surface enhanced Raman scattering. Okay, so if you combine SIRS and also resonant Raman scattering means the metallic surface and the laser frequency are same, then you have resonance. Then it can even go up to enhancement factor up to 10 power of 10. Okay, so this is and even I think higher recently from some study they proved up to 10 power of 12. So 10 power of 12 is considered approaching single molecule scattering. Okay, so this is the whole idea. So the nanoparticle surface, so you have compound on the surface, laser came in, so it creates an enhanced near field, the electromagnetic field on the surface. Okay, so and the compound will emit the scattering because of this enhanced field. So the signal will be increased tremendously. So and study slowly conducted over time, then they realized that the field is actually, the enhancement is by the nanoparticle is mainly due to several factors. It could be due to the sharp edge, okay, sharp edge of the nanoparticle, sharp edge, or maybe some point of contact between the particle and particle that gives you the enhancement. Actually, I noticed one phenomenon at home when I try to defrost fish ball which I took from the freezer. I took fish ball from the freezer, then it turned into ice, so hard. So before I cook the noodle, so I had to thaw. I had to melt the ice, right? So I use domestic microwave. I put the two fish balls in the microwave, then I heat it up to maybe 10 seconds. And I take it out, then I notice that in the middle here, they turn into dark and yellowish color because of maybe overheat. So I think that kind of effect, because the microwave, domestic microwave is also wave. So means that the heat generated concentrate at this point because of their surface area is so high. So they touch it with one another. So that spot actually discharge the water, and the water being heat up by the microwave. So that's why that area, that contact point turned darker. So I think that could be more or less the same explanations. So, and many studies, actually, they realize that you can enhance a factor up to 11 if there is some overlapping, because each single nanoparticle will have their own electric field surrounding. When they touch with one another, that electric field will be overlapping, so even increase the field strength. So that's the reason why enhancement happen. Okay, so not many transition method or method give you this kind of functions or characteristics. Only 3 so far. Okay, copper, gold, and also silver. These 3. So the most popular one is these 2, copper and gold and also silver. Copper less because of many reasons. Because I think the most important reason is because copper is oxidatively unstable. Copper tends to be oxidized very easily, okay, much easier compared to gold and silver. Even silver will oxidize, but not as serious as gold or as copper. So gold is the best, then followed by silver. So if you notice, the plasmon resonance, surface plasmon resonance of gold and silver actually around visible light. Okay, all are visible light. That's why you can see silver nanoparticle color changing from blue to red. Okay, blue to red because of the plasmon resonance. Okay, so means that if you use gold, if you use silver, then the enhancement, the laser enhancement should be happen near this range, and also gold. Okay, these are the range. So what are the advantages of SIRS? So how to use it? So very simple. So you have a substrate. Okay, you have let me show you the figure. Okay, this is these are commercial available SIRS substrate. Okay, I just type keywords in Google, then I obtain many. Okay, so these are silver from Silmeco. They fabricate or they sell the silver substrate, SIRS substrate. Then you drop the analyte on the substrate. Then immediately after the draw, you dry, You dry the substrate, then you immediately can check. So under the microscope, you can see the silver actually aggregates and form pillar. So the compound, after they dry, they will stick on the surface. So concentrate, and when you strike the Raman laser, then scattering will be enhanced. So Ocean Insight also selling, Nika also selling gold as a substrate. It's just a substrate, very simple. You drop your analyte, the whatever compound in liquid form onto the substrate, then you leave it dry, then you can shine it under the micro Raman spectroscopy. I think the best would be definitely using micro Raman, the microscope. Okay, because this spot going to be, you will turn into very small spots after dry off. Then you can observe it under microscope. So non-contact and non-destructive, okay, then high sensitivity and high specificity, okay, because each compound will have their own fingerprinting, and this is very selective. Okay, then no sample preparation, just drop and leave it dry. Then both organic or inorganic substance can be measured. Then liquid, gas, solid can be used. Okay, then fast 10 millisecond to 1 second exposure because of the enhancement. Then imaging analysis is also possible. So various field you can use. I think the most useful, I believe, is the forensic, because you want to check. People have been using it for drugs in the custom airport to check the trace amount of drugs, methamphetamine from the luggage, from the handbags. So you have a search substrate, you can just swipe it on any surfaces like pocket or jeans, your clothes, whatever trace amount of the methamphetamine or drugs can be easily enhance the signal using search substrate. Okay, this has been using in the real scenario. Okay, so the environmental detections, people also develop search substrate for cancer cell. Okay, cancer cell detection, and they're able to differentiate first stage, second stage, third stage, or fourth stage of cancer. So by obtaining the cancer cell spectrum, the Raman spectrum, then you can kind of estimate which stage actually the cancer patient is. That is very useful. So, and also SARS and COVID virus can also be using a search substrate for the detection, because it only requires trace amount of the compound. So if you still remember, 10 power of 11 of enhancement. So that is very powerful. So how to fabricate? There's been many various types of method developed. Even our group, we also developed several types of protocol, how to come up with the substrate. So you can use very advanced lithography method to align or to arrange the nanoparticle or the silver or gold nanostructures in orderly, or you can use electrochemical method just to have depositions. Okay, very quick one. Or you can use galvanic displacement. Okay, galvanic displacement, just drop copper or copper chloride, copper sulfate on top of a coin, a silver coin or zinc or brass coin. Then they will replace one another. Then gold will be precipitated, forming a rough surface, because gold is also can be act as a surface for enhanced search. So this is also possible. You can use inkjet printing to print the colloidal silver nanoparticle on paper. So the nanoparticle will stick on the fiber of the paper. Then you drop the analyte on the surface, leave it dry. So when you shine the laser, the nanoparticle aggregation, okay, the aggregates will create the hotspot for enhancement. So it actually from high-end, high advanced method until very home, you can do it at home. So this is a very, I think, quite versatile. Okay, very straightforward method. Okay, so this is one I mentioned to you just now. So we can use galvanic. So people using it, this kind of substrate. This study actually tried to detect melamine. So if you remember, many years ago in China, there are scandal about this high protein baby formula, this milk powder, formula powder. they add in melamine powder just to cheat and to sell the milk as a high protein content milk powder. So how to detect? Most of in conventional method, you use kejar method, so which is very time consuming. You need to digest the nitrogen compound, the protein or the melamine into nitrogen. So simple nitrogen. Then you only can determine the protein content or nitrogen content. But using just a little bit of the powder, even in liquid form, you just drop on the substrate, you shine under the Raman, then immediately you can get the melamine spectrum if there is certain concentration of the melamine powder in the milk form powder. So very useful. Okay, very useful. So even for bacteria, okay, you can check E. coli, Staphylococcus typhi, penicillin resistance Staphylococcus MRSA, and also many other types of bacteria can also be easily identified using this substrate. Okay, so I see I found it very useful. Okay, very versatile. Okay, so and also an example of bacteria. Okay, so these are a couple of examples. So just want to convince you that although conventional Raman spectroscopy has many limitations, but over the time when we do research and development, we try to explore, we try to improve, and even new material being developed. So new method, so you can actually solve many limitation or disadvantage of existing conventional Raman spectroscopy. So now new term has been introduced, which is we call it surface enhanced Raman scattering. Okay, so I have actually slide, but I don't think I have time to cover it. I think especially on my own research, but never mind. I think I already shared the slide to Mr. Sahriab, so you can maybe obtain just request a copy. Then if you have any questions, please don't hesitate to contact me. This is my email, so we can discuss. Okay, so if there's any potential work we can do together, so I always welcome. So thank you for your attention. Thank you.
Thank you so much, Prof, for your wonderful presentation. So, like, I want to share one slide. Could you please stop your sharing, Prof?
Yes, sir.
So, I want to know, like, this is actually Raman picture. So, I get from the analysis center. So, in that case, where we should focus on, Prof?
Okay, Mr. Sarah, I think from this figure, I noticed this should be optical microscope image.
Okay.
So if possible, if the sample is still with you, then I suggest you to request the operator to run again, take a new optical image, then don't shift the sample, then directly convert it into Raman analysis. So can choose an area, not necessarily take the whole image. We can just focus on the center point, maybe
Okay.
a square, yes.
Just so we need to focus on just this center point, right, Prof?
Yes, you are right. Then ask the operator to obtain the Raman image. But before that, Mr. Sarah, ask the operator to run a single point measurement of Raman. Then you check whether the 0% up to 12% compositions give you significant difference in terms of the Raman spectrum. Yes. Then only you ask him or her to extract or to obtain the Raman image.
So in that case, Prof, if we can see that from signal, there are not significant difference between actually 0 to 12. So what we can say? We can say that the material, similar material, it doesn't affect of the doping.
No. Okay, so I think if the objective of your study is to analyze the effects of doping, then I'm afraid that you may not able to get good result because doping normally happen at atomic level.
Yes.
Atomic level is way far from this microscope scale.
Okay.
Yeah, unless you are doing some kind of like surface coating or maybe a composite material with different phases, then at micro scale, then you may able to see the difference. But doping, I believe you should go for EDX or XPS.
So in that case, we can say that if we can see that from 0 to 12, we dope, and then 0 to 12 is similar signal. That means that our main materials, for example, RGO is the same.
Yes, yes.
Yeah, and also structure also same. There are no
Yep.
significant difference between the synthesis process, because when we do the synthesis, maybe due to the doping or maybe the percentage of the RGO reducing graphene, so it's not changes. We can confirm by the Raman.
Okay, yes, you are right, Mr. Sarah. And also, don't forget about the D band I mentioned just now. The D and G band will also, yeah, D and G band will also affected by the doping, because doping is some kind of defect.
Yes.
Right, defect. So defect will change the G significantly and also create a high intensity in terms of the D band. Yes.
And
so
Prof, I have one more question also, because you mentioned about D band and G band, and I have seen that some article they also explain about the 2D band.
Yep.
2D, yeah.
I also mentioned just now, 2D band tells you about the number of layer also. But from the image you share with us now, I can see that the material actually clumps together quite significantly, and they may already stack into some sort of layer form. So I think the D band, the 2D band may not be so significant anymore. Yeah.
Yes, Prof, you are right, because from the peak, I can see that there are not too much effect on 2D band, but we can see very small amount is after 2,500. If we go to the very lower, then we can see little bit about the 2D band, but it's not visible actually clearly.
I see. So what kind of doping you're trying to do for this sample?
We dope proper the aluminum.
I see. Okay, the previous sample.
Yes, Prof.
Ammonium. Yep. And I think another thing, I think you can try. I think SPS would be quite
SPS.
XPS, because doping is a very small, I think is down to molecular atomic level. And
Yes.
I believe if the sample was were washed thoroughly, then you already remove most of the undoped or free ammonium ion. Then whatever signal obtained from the from the XPS, and we can confidently tell that those nitrogen binding energy is contributed by the doping. Yeah.
Yes, Prof. We identify by EDX. And also the powder we analyzed by the EDX mapping. So in the mapping also we can see, today you mentioned about mapping, and I was confused before about the mapping, like why 7 different picture. And so mapping, we can see the concentration of doping and the alignment of the main materials, like we dope with zinc, so we can see how much percentage, depends on percentage, how much effect on the surface. We saw the EDX mapping.
Yes. It's true. True. Mm. Yep. From 0% to 12%. So you found it significantly increased in terms of the mapping result using EDX.
EDX we found from the percentage of doping like for 0%, we have seen little bit contamination due to the we thermally actually that reduce the graphene. So maybe it possibility from previous experiment something like the contaminant, but we can see the significance like consistency like 4%, we can see maybe 1% and 6% it become a 2 point something or 4%. So we can see the significant difference between the all concentration. But at the same time also we found one thing different, that the contamination of 0%, because 0% we did not dope, but we can see some the aluminum atomic something yeah, particle something in the 0%.
I see. Yeah, it's very difficult to avoid that, because I think sometimes we share the equipment, we share the instrument, so that is also
so maybe Prof, I can share with you the file of our just picture.
Yes, sure.
Okay, then you can. This is actually for graphene pop EDX, and we can see also this is the mapping. So the carbon, oxygen, silicon, aluminum, and this is actually contamination from previous. So we separated different concentration, and based on the concentration, we can see the significant changes between each. And this is the Raman Pro.
Oh, okay, I see. So 0%. Yeah, not much effects.
Not much effect, but after 2600, then here we can get some. It's not a high peak, very low, but the finding is that it might be possible 2D.
You're right.
Because here we can see that it's lower, but from after 2500, the peak going up little bit.
Yep, true. Have you calculated the ID over IG?
Yeah, I'm calculating like ID minus IG is equal to the 2D, right, Prof?
Yeah. The ratio. So the intensity,
yes.
the ratio. So you
ID divided by IG.
Yes. You see whether are they the same. I think from the by naked eyes is more or less the same, not much different.
Yes.
I think I believe this could be due to the starting material that you use. I believe is graphene oxide.
Yes.
So graphene oxide is, I think, if you follow my presentation just now, when I talk about the Hammer method, the experiment, we try to oxidize the graphite into graphene oxide, right? The Hammer chemicals, the potassium permanganate, the sulfuric acid, is so strong. It basically within 15 minutes it destroys the whole structures of the graphite. Yeah, so it destroys the graphene structure. So and eventually when you dope with the aluminum, it becomes no longer significant anymore.
And we can see also, Prof, if we compare with XRD. Yes. So here we get actually the indexing is same, but we got the peak is not
Oh,
If you
yes,
compare the
yes, yes.
literature review, it's not a RGO like normal RGO. So when I can compare with the thermally reducing graphene oxide, it's quite similar like this. So we did in the tube furnace, right? So they are also like little bit different, between the reduced graphene and after doping. There are
Yep, I see. Yes, I see. Yes, there are some, you can see a bit of a shift.
shifting little bit, bro.
There
Very
be shift.
small shifting.
Okay, so yeah, interesting, Mr. Sarah. So what else of analysis that you conducted on this one?
Yeah, this is the TM result, bro.
Oh, okay. You run HRTM.
Yes, TM. We also TM for each. And
Where
this is
where
the
you access the HRTM, Mr. Sarah?
TM, bro.
Yes, the HRTM. Yes.
TM we did in our scientific equipment center
I
in
see. So
Thailand.
I see you have the instrument.
Yes, bro. And this is the actually EDX result for 4 difference.
Okay. Good news. You have you have the increment of aluminum content, the percentage.
Yes, bro. And here we can see that carbon when 0% is 50 and it's rapidly going down when we increase the concentration of the aluminum.
But the silica content is also getting higher.
Yeah, I think it's a contamination, Prof.
Yes.
Because we did in the tube furnace, so we don't know the inside the tube furnace.
Yeah. What is the what was the substrate that you used to hold the graphene oxide powder?
Ceramic, Prof. Ceramic plate.
Ceramic plate, huh?
Yeah, ceramic plate.
Okay.
It was open, Prof. It was open, not like closed. So
No.
that's
I mean during the EDX analysis.
Oh, EDX analysis, we did it for this is for maybe, this is for Prof the thin film.
In what, in the film? Silica, the glass or what?
Oh, yes, a glass, Prof. Sorry.
So that is the background. That is the silica.
Yes, that's the background, Prof. Yeah.
So you can remove this one. This is considered as the background. Yeah.
Okay. So I remove this one because it's actually the glass. I forgot to.
Yeah. This is from the glass.
But here we can see the problem. The biggest thing is that the contamination of during when we compare with powder, in powder is not too much contamination. It's 0.2. Here I can show you. Here we can see only 0.2 contamination in the RGO.
I think you should use. I think you should use this one instead of that one.
No, it's two different prop. This is for powder, and that is we deposit a thin film.
Oh, I see. No. Because you are, in my opinion, because you what are you trying to report? Report now is in terms of the doping efficiency, right?
Yes.
So if the doping efficiency, you should get it from the powder, because the powder basically cover much better during the analysis. The powder sample basically cover more area compared to the thin film, because the thin film sample you may not have enough sample to cover up the whole area of the analysis. So the result become not accurate.
Yes.
Yeah, I think my opinion, you should use the powder result instead of the
this is actually proper thin film one only for
also you convert it into thin film sample already.
Yes.
Okay, I see.
And my finding is that I can explain the negative result of this, that explain that we should be careful about during the deposition process. Otherwise it might be contaminate our experiment, and it also reduce the efficiency of solar cell. if we
You're right.
use
You're
the
right.
ECM layer. So
Agreed.
here we can see prop but on the other hand 6%, 8% we can see that it rapidly increasing because the aluminum doping.
Aluminium doping. Yes, you're right.
Yes.
Yes, you're right. Yep. Good.
And this is the SCM result, like this is 0% and 4%, 6%, 8% and 12%. And we can see, I think we can see the this is actually thin film SCM. So we can see the aluminum particle also, some big particle on deposit, because due to the when we deposit in our lab, I think some particle size was bigger because we use the spin coater, so maybe it was not aligned properly.
Yes, you're right. You're right. Because from the SCM images you showed just now, the graphene, reduced graphene oxide is actually basically they form clumps. They
Yes,
from
Prof. And
agglomerate.
the surprising thing is that, Prof, we calculate by mathematically, theoretically calculate the deposition of graphene, that by using we use each only 150 micron liter for, and we theoretically calculate it might be possible to 100 to 120 nanometer. So from SCM cross section we can see the thickness of the thin film is almost similar. And because we use same amount of solution for each deposition.
I see. I see. I see. So the top layer is the coating that you
Yes,
managed
yes,
to.
yes, Prof.
Oh, that is very nice layer.
Yes, Prof.
Oh, okay, very good.
And this is the FECM. Sorry, EFM result. So that's actually for the we have total 10 characterization for each sample.
There's a lot. There's a lot. I think quite very comprehensive study. Do you have XPS in this case?
Oh no, we did not add we discussed with Lau that he said that if we do the EDX, we don't need to do the XPS.
I see. I see. I see. I see. Understand.
And for zinc oxide we have 10, because and also graphene we have 10, to it would be 20. And at the same time we are going to add some simulation part and also DFT for each concentration. We just calculate the band gap by using DFT.
I see. I see. I see. Interesting. Interesting. So you're right. If you submit send sample for XPS, it's going to be a lot of sample.
Yes, Prof. At the same time, I'm preparing 2 manuscripts, Prof. For one for graphene, one for zinc oxide. So when I submit the thesis, at the same time, I will submit manuscript too.
Very good, Mr. Sarah. Very good.
Thank you, Prof. So now, audience, I think if you have any questions, so feel free to ask. Not only that, from our topic, you can talk about from outside also.
If you have question, you can also maybe later you can email me also, no problem. We can discuss.
Yes, Prof. Yes, Prof. So I think we from audience we don't have any questions, so we can conclude our session. And thank you so much, Prof. Please send me the slide and then I will share with all of them.
Yes, yes. I think I'm not sure whether you receive it. I just send it to you. Do you have this copy in using WhatsApp? Yes, I send it. I think you try to check. If no, I will send it again. Yes. Yes, I sent by WhatsApp already. You can try to check. Yes.
Okay, Prof. Okay, Prof. So thank you so much, Prof, and see you again.
Thank you everyone. So it was nice sessions.
Before
Sessions.
you leave, just one picture.
Sure.
Okay.
So thank you for all the attention given, and so I enjoy very much. So I learned together with you all. So hopefully we can have we can meet each other like in coming future. Definitely meet each other. We'll meet soon.
Yes, Prof. We will meet soon, Prof. Thank you,
Thank you.
Prof.
Thank
Okay.
you. Take care.
Bye-bye.
Take care.
Bye.
Bye bye. Bye everyone.